putting together this workshop. So Walmart has funded us generously for these kinds of events, and I've heard my colleagues say that they would like to sort of replicate the Dakshtul experience or the Simons Institute experience. I hope you have such a good experience here. For those of you that are visiting the institute for the first time, do take some time off to walk around the campus and to learn about the history of the campus. And for those of you that are visiting CSA as a repeat customer, welcome back. With that, let me hand the proceeds over to Professor Jayakumar.
He will know about himself.
So good morning, everyone. It is my pleasure to welcome you to the first session of the Graph Algorithms workshop and to introduce the session's speaker, Professor Jayakumar Radhakrishnan. Professor Jayakumar completed his PhD at Rutgers University in 1991, and he has been long associated with TIFR, where he is currently a senior professor. He is a recipient of the prestigious Shanti Swarup Bhatnagar Prize in Mathematical Sciences. His research has made significant contributions across several fields of theory CS, including combinatorics, information theory, communication complexity, and today's talk is also based on that. He is also widely respected for his humility and for the guidance he has offered to many, many students. With that, I invite Professor Jayakumar to deliver his talk. Thank you.
So good morning. Thank you for the introduction. Part of it I missed, I'm sorry. So the idea is that this is going to be a boot camp session, and circumstances have somehow made me give the first talk. So it will be on communication complexity, perhaps not the central focus of this workshop, but there will be many talks which will refer to communication complexity, and I'm hoping that this review will help you understand those talks. So the plan is I'll tell you what is communication complexity. For a good fraction of the audience, this is superfluous. But those who have not seen communication complexity, I hope you'll benefit from the first part. And I will at some point try to justify why communication complexity at all in the context of graphs. And then I will just review the standard terms and concepts in communication complexity, how lower bounds are proved in communication complexity, the various models of communication complexity, that is the deterministic and randomized versions. And every now and then I will throw in a problem about graphs, which the communication lower bounds for which follow from standard problems that are studied or have been studied in the past in communication complexity. So what happens in communication complexity, at least in the two-party communication complexity? There are two parties, Alice and Bob. Alice and Bob. And Alice receives her input from a set. This is meant to be script X, and Bob receives his input from a set script Y. And the problem itself is to compute a certain function. And the trouble is that the function depends on the two inputs, and the two inputs are not available at a single place. Yeah. X is with Alice and Y is with Bob. And so they need to communicate. Someone has to send the first message, someone needs to send the second message, and so on. And eventually, one of the parties or both of them have enough information so that they can tell what F is. So that is the problem. And what's the solution to this problem? The solution to this problem is the protocol. Yeah. That is, given the inputs, how are the messages to be generated so that in the end they have enough information to compute F. All right, that's the solution. And what is complexity? So the complexity is we would try to reduce the use of resources. And in our case, one of the things that we would like to minimize is the number of bits exchanged. So they would like to come up with a protocol so that the number of bits they exchange is as low as possible. There are situations where other resources, the number of alternations between Alice and Bob is to be reduced, and there might be other restrictions on the way they can communicate. So, but mostly, I think if you think of minimizing the number of bits exchanged, that will serve well for most of the talk. Yeah. So one of the, so that was an abstract problem, but here is a concrete sort of graph problem, not yet fully concrete. So here's a graph, and some of the edges, let's say the red edges, are given to Alice, and the blue edges are given to Bob. And then they need to communicate in order to determine perhaps whether the graph is connected, whether the graph has a perfect matching, or whether it has a min cut of a certain size, or what is the value of the minimum cut, non-trivial cut in this graph. So these are the sort of questions that will arise when we think of communication complexity of graph problems. So this is the mandatory sort of slide on why graph theory. So why communication complexity for graph problems. So communication complexity itself arose in the study of VLSI layouts, where we would like to understand the trade-off between the area needed to lay various elements of the circuit. Hey, nice to see.
Were you?
No, it's okay.
Are you in the middle of the?
Yeah, in the beginning. Yeah.
Okay.
Yeah. So it was VLSI layout initial. So you could use communication complexity lower bounds to show that if you try to have a VLSI layout of small area, then it would necessarily take a lot of time to finish the computation. One can imagine that the graph that you have is laid out and the information about the various parts of the graph are with various agents and they are distributed, and in that case perhaps communication dominates the cost of computation. So clearly communication complexity is a useful model, but perhaps there you would like to consider communication complexity with multiple parties. Communication complexity has also been used, and like spectacularly, in showing that hard problems cannot very naturally be embedded or turned into linear programs or other fancy things that we know how to solve. Okay, and this is somewhat counterintuitive. I mean, somehow, yeah, communication complexity makes an entry into this field, and it's one of the remarkable connections between various areas of complexity theory.
What's a specific example here?
So I think the TSP doesn't have a small
The extension.
extension complexity. I wanted to avoid the long word. So various other models where there is restriction on the flow of data, for example, streaming and other areas of modern computing. So they can be analyzed using communication complexity, and communication complexity, at least lower bounds in communication complexity, have things to say about space complexity, circuit complexity, data structures, and so on. Okay. So in general, it's an important field, and every now and then it shows up in a surprising way in an area where it was not suspected to have any role. Okay. So that's my standard apology for subjecting you to this. But
They avoided randomization so far.
so far I have not mentioned randomizations, but I will talk about both areas of both parts of communication complexity, the deterministic one and then the randomized one. Okay. So yeah, so I'm assuming for many people this is new, so I'm kind of starting at the beginning. All right. So probably the first problem in communication complexity. So Alice has an X, Bob has Y, and they need to tell whether X is equal to Y or not. So here the set script X is 0, 1 to the n, the set script Y is 0, 1 to the n, and the set Z, yeah, is just 0, 1. It's a Boolean function. And I mean, there is a natural protocol, that is, Alice can just send her entire input over to Bob, and Bob can check if X is equal to Y and return the answer to Alice. And that would require n bits of communication. And I mean, intuitively, at least, it's clear that if you want to check the equality of two things, you ought not to be able to do anything better than n bits. And it turns out that one can prove that n bits are necessary. So there's no way you can compare X and Y by somehow cleverly alternating and exchanging messages with fewer than n bits. So just I would like to sort of go over this lower bound in some way. So how does one prove that fewer than n bits of communication cannot do the job? So with every Boolean function, you have a matrix where the inputs of Alice are laid out along rows, the inputs of Bob, the potential inputs, are laid out along as indices of the columns, and in the entry corresponding to X and Y, you write down the function value. So this is sort of the truth table of the function, except that the input is in two parts, so we write it as a matrix. Okay, so nothing remarkable. Now, a protocol, I mean, has been defined somehow abstractly. That is, a protocol specifies how subsequent messages are to be obtained based on past data. Okay, and what is past data? The previous messages received from the other party, and perhaps the input that you already have access to. Another way of visualizing a protocol is to draw this tree. It is like a decision tree, except that the decisions are made not always by the same party. So suppose it was Alice's turn to speak first, then we write Alice at the root, and based on her input, she now decides to go left or right. Left in our minds means she decided to send a 0 to Bob, and 1 means she decided to send a 1 to Bob. On receiving this message, one can figure out, or receiving this bit, one can figure out whose turn it is now, and perhaps Alice continues speaking, or she hands over charge to Bob, at which point Bob, based on the fact that Alice has sent him a 1 and his own input, decides to send the next bit. And this goes on, and at the end, we reach a leaf where the answers are stored. Okay? And to say that we have a protocol, or to say that we have a tree like this, is the same thing, because if you have a tree, Alice and Bob can both share the tree in advance and then walk down it when they actually receive their inputs. Okay. So for a specific input, the computation takes a certain path down the tree. And in the language of trees, it is a path from the root to the leaf. In the language of protocols, you call it a transcript. And what's a transcript? See this yellow band here is the transcript, and it consists of the various bits that were sent. Sorry, obvious. Yeah. So first it was 1, 1, 0, 0. Okay. 1, 1, 0, 0. So this is what we mean by a transcript. Yeah. So that. Now, so again, back to the old setup. So you had this matrix, rows indexed by x, columns indexed by y, and suppose Alice sent the first message, then she would send zeros for some of the inputs and ones for some of the inputs. So she sort of tells Bob whether she's in this part of the matrix or this part of the matrix, whether their joint input is in this part of the matrix or this part of the matrix. And then it's perhaps Bob's turn, and Bob decides to tell Alice whether it's on this side or this side, and if it is on this side, Bob again tells Alice whether to go this way or this way, at which point Alice decides whether to go this way or that. And once they reach the end, the leaf, what we have here is a rectangle like this, and all the inputs in this rectangle have the same answer. That is the reason why they don't need to further subdivide it. They have reached a stage at which the answer is determined. Okay. Now you can imagine that if you have a particular transcript and you ask which inputs lead you to this leaf. Yeah? So there are decisions that were made by Alice. So Alice to get to this node, Alice needed to cooperate. That is, whenever she was given charge, she should have gone in the right direction. Okay. So all those inputs of Alice, which would which would cause Alice to cooperate, that is one set. And all those inputs of Bob, which would cause him to stay on the path, they are another set of inputs. And if you pick any input from this set and any input from this set, nobody would have an objection, and they would still continue on this path. So this is another way of saying that the set of inputs that lead to a particular leaf, they correspond to a rectangle. Yeah? Those inputs where Alice has no objection, and those inputs where Bob has no objection. But if you had already started imagining the workings of the protocol in this fashion, it is clear that this is rectangle. Yeah, so a standard sort of disclaimer. Of course, things need not be contiguous. Yeah, the set separated here. So these are generalized rectangles, yeah, cross products of subsets of the rows and subsets of the columns. All right. So one of the reasons why a communication problem might be hard is that the matrix that we have been given. So how have we been given the matrix? The moment the function is specified, the matrix is there. but it may be very hard to divide up the matrix into rectangles. So if you have a small protocol with few leaves, then you will have a way of decomposing this matrix into a small number of rectangles, where in each rectangle the inputs have the same function value. So to show that a problem is hard, we need to establish that there is no easy way to break up this matrix into rectangles, where within each rectangle the answer is always the same. So there are many ways to show this, at least in deterministic complexity. So I just want to mention a few things which perhaps will come up in other talks too. So one of the things is, one of the objects that is used in showing lower bounds is fooling set. Okay. What is a fooling set? It is a set of inputs. So I just give you a set of inputs, and I somehow need to argue that no two of them can be put in a common rectangle. Okay. So when you see an example, it will become clear. So if I can show that there is a large number of inputs, a set S with many inputs, but no two of them can be put in the same rectangle, then clearly the protocol tree must have as many leaves as the number of elements in S, and if it has that many leaves, it must have log of that much depth, okay, and that would tell us that you would need a lot of communication. Okay. So one way of showing lower bounds for deterministic protocols for problems is to study this matrix and come up with a fooling set. Now let us implement it in the case of equality. So what was the equality problem? You were given an x and a y, so 2 to the n. There are 2 to the n inputs for Alice, 2 to the n inputs for Bob. And when are they supposed to say the inputs are at the diagonal? Okay. Now, consider these 2 to the, so I'm trying to build a fooling set for the equality function. Okay. So again, it's probably completely obvious to everybody, but let me go through the motions. Consider these inputs. So there are 2 to the n cross 2 to the n inputs, but only consider the inputs that appear along the diagonal. Okay. Now, my claim is that when the protocol finally decomposes this matrix into rectangles, no two of them can appear in the same rectangle. Okay. And it's more or less obvious, because if you try to put two of them in a rectangle, in this and this in the same rectangle, then this input will also fall in the same rectangle. But the output, you see, the rectangle was something that came from a leaf of the protocol. So all inputs that belong to the rectangle must have the same output, but the output here is 0, whereas the output at these 2 points was 1. So the rectangle could not have a common output. So yeah, it's a kind of obvious thing. So no matter how many rounds they take, etc., in the end it's a rectangle decomposition of the matrix, and these inputs, we have now concluded, must appear in different rectangles. You would need at least 2 to the n rectangles, so you need n bits of communication. So there's a kind of more sophisticated argument somehow into this problem. Okay. So when you have a matrix, you might, all your linear algebraic juices might start acting up. So especially when you have a 0-1 matrix, you might start thinking about its rank as a linear algebraic quantity. Okay. And it turns out that somehow the rank of the matrix associated with the function has something to say about its communication complexity. And the reason is this. So focus on the ones. Yeah. So you had a communication matrix, and it had ones in some places, zeros in other places. And in the end, look at those rectangles that cover the ones. Yeah. So you had one particular leaf where 1 was written, that corresponded to a rectangle. Draw that rectangle. Okay. Of course, not necessarily contiguous, it is some cross product. Then for the next transcript, which gives the answer 1, you have another rectangle. And you have another rectangle. And write zeros elsewhere and add these up as matrices, let's say over rational numbers. Now clearly, this gives you the original matrix of the function. Okay. Now, each of these is a rank 1 matrix. Yeah. So each of these is a rank 1 matrix, and together they produce a matrix which is the matrix of the function. Now, yeah, I let you check that if you add two matrices, the rank, is at most the sum of the ranks of the constituent matrices. So if finally you have a high rank, then you must have had many such terms in your sum. If you had many such terms in your sum, then it must be the case that you had many leaves in your protocol, because each one of them is for a separate leaf. Okay. And if you had many leaves, then log of that number will have to be a lower bound on the communication. Okay. So this tells you that the communication complexity of a function of this kind, Boolean function of this kind, the log is a lower, log of the matrix is a lower bound. And yeah, so whether some reasonable function of log can be put on this side. So is it in the end that communication complexity is some sort of a complicated way of linear, it's more or less captured by linear algebra. That is still an open question. Yeah, it's called the log rank conjecture. Whether communication complexity can be bounded by a polynomial in the log of the rank of the underlying matrix. Very deep sort of theorem. Yeah, so conjecture. But in any case, this gives a relatively painless proof of this fact that equality needs n, because the matrix for equality is the identity matrix, and identity matrix is a full rank matrix, so it is the rank is 2 to the n, log of that rank is at least n, so communication. So this equality problem, yeah, has we have seen two proofs. One is the fooling set proof, the other proof is via the rank lower. Okay. Question?
Is this stronger than the fooling set log n?
Yes, there are situations where you can prove it using the log rank. I'm not able to recall an example immediately, but yeah. So it's not as if, so we will see an example right now where we will make crucial use of log rank, and at least in that example I don't see immediately how to build a fooling set. Perhaps there isn't one. Okay. Yes. You'll just see. Yeah. Questions? Yeah. Yeah, please keep asking and saying simple things. Yeah. Question there.
For every fooling set element,
Yeah.
we convert it to a corresponding rank.
Every fooling set element. Okay. So, yes, a fooling set is a set of inputs, yes, and
Yeah, I was saying that can we say that the fooling set argument can be,
converted to, if we
Yes,
restrict
one
ourselves
is-
only to the fooling set, then it looks like an identity matrix then.
Yes.
So that, in that sense, the fooling set argument can always be cast as a rank argument. That's good. If a big matrix has a small identity matrix sitting inside it, then yeah.
What does the log rank translate to in the fooling set world?
No, I'm saying that if you had a fooling set argument,
Yeah, for the lower bound.
yeah, and you had a lower bound, let's say for 0, 1 matrix, basically it amounts to a little identity matrix sitting there. because these are inputs.
Which the
Cross terms are not there. So since a big matrix has a little identity matrix sitting inside it, its rank must be at least that much, and then the log of the rank would give you the same.
So that answers my question, I can say that rank arithmetic
Is not weaker. Yeah, I agree. I mean, but I need to show you in a place. Is it true that the only reason a matrix has high rank is because there is a little identity matrix sitting inside it? Probably not. You can imagine. Yes. So this is one of the classics from the 80s, and I want to tell you about this. So yeah, so finally back to this workshop. Yeah, so about graph problems. Okay. So I'm going to say something which do not look like graphs immediately, but very soon. So I'm in the end heading to a lower bound for connectivity. So yeah, so some combinatorics. So we have a set n, 1 to n, and Alice gets a partition of 1 to n. Partition means a collection of subsets, all non-empty, disjoint, whose union is the whole set. Okay, so this is one partition. And Bob gets another partition, maybe with a different number of sets in it, but all of them are non-empty disjoint sets. Now, consider the 0, 1 matrix M, where the rows are indexed by partitions of Alice, partitions that can be given to Alice, and columns are indexed by partitions that will form the input for Bob. And in the entry corresponding to PQ, you write a 1 if, so think of connected components. So P and P represents the connected components of Alice. Q represents the connected components of Bob's graph. If you put them together, new connected components form. Yeah. That also is a partition of the set 1 to n, and that is called P or Q, or P joint Q. Is it clear? So it is that partition, what did I write? The finest partition, yeah, of which both P and Q are refinements. Okay, so this is, if you want to avoid the word graph connectivity, this is how you would say it. But think about it as connectivity. These are the connected components of Alice's graph. Those are the connected components of Bob's graph. And when you put them together, some connected components merge, yeah, and you get a new set of connected components, and those then viewed as partition. So now this is a matrix which has zeros and ones in it. So you can ask what its rank is. And a rather deep theorem in combinatorics due to Dowling and Wilson says that this is full rank. So because this is full rank, it would have a rank as much as the number of partitions that exist of a set of size n. Now this is the Bell number, but we probably don't need to know it exactly. So let us just say, so assume that this is a large number. Okay, the number of partitions of a set is a very large number, and so the log of it, which will eventually form our lower bound, will also be a large number. Okay, so with this sort of hope, let us try to build graphs which turn this fact into a concrete lower bound for connectivity. So what's the graph? Well, Alice picks a partition, yeah, and if the partition has, let's say, L parts, she takes the first L vertices here, connects the first vertex to the vertices in the first block of the partition, the next vertex to the vertices in the next block of the partition. Is it clear? Yeah. And the remaining vertices, which are somehow orphaned here, maybe she just connects them back to this. Now Bob does the same thing. The number of blocks here is k. and the first vertex is dedicated to the first block, the second vertex for the second block, and so on. Now, if you put, so these are the edges given to Alice, these are the edges given to Bob, and if you put them together, sorry, what? We will get a connected graph if and only if this partition joined this partition is the trivial partition consisting of the whole thing. Okay. So we have somehow faked it. The communication complex, if you could solve the connectivity problem, yeah, then so the matrix corresponding to this set of special inputs that we are creating here has rank as much as the number of partitions. Now I'll let you check that the number of partitions, if you take the log of it, it has to be, I mean, let's say you take the first square root n elements, and every other element you put it in one of these bins corresponding to the first square root n. So the number of ways you can do this is perhaps square root n to the power n minus square root n. Okay. So you do have a large number of partitions, and since you have a large number of partitions, the rank is very high, and the log of that rank is very high, and you need n log n bits of communication. So this gives you a way to show that connectivity requires n log n bits of communication, and this n log n is tight because when Alice gets a set of edges, she just looks at the connected components, and each of the vertices she labels in this number of colors, at most n colors. All the vertices which are in the first connected component are colored 1, all the vertices that are in the second connected component are colored 2, and so on. And she just sends this coloring to Bob, and Bob, based on his input, can tell the answer. Okay. So how many bits? Yeah. So how, at most n log of n to the power n. But so this was a result of I did not mention perhaps Heinel, Maas, and Turan from the 80s. But they actually proved something even deeper. They said, take the complete graph. This is the complete graph, and half the edges you keep for Alice. You don't give for, you keep half the edges for Alice and the other half for Bob, and Alice will be given an arbitrary subset of edges of these, let's say the red edges. There are some edges which are colored red, some edges which are colored green. Some subset of red edges will be given to Alice, and some subset of green edges will be given to Bob. And you can choose which edges to give to, which edges to be colored red and which edges are to be colored green, no matter how you partition the edges between Alice and Bob. Okay, the problem remains hard. Okay. And again, deep theorems from graph theory come into play, are combined with a deep theorem about algebra in the end. So what Heinel, Maas, and Turan show is that when you have any such partition into two dense graphs, you can construct inside them a gadget of the kind that we had here. Okay? Except that here we connected them with a straight edge. Here there might be some paths of length 3 or 4. So whenever you have dense graph, you can partition them so that you can get the gadget that we had in the previous example, no matter how you partition them into half of n choose 2 edges each. Okay. And because that is true, you can always play this game that we played previously and derive an n log n load. So it's not just for your chosen partition of neurons. No matter how you divide this into two parts, you would always need n log n.
What is used, like the Towling-Wilson result that you mentioned in previous slide, how is that done?
Sorry, how is that?
What tools do they, is it purely linear?
So this, yeah, so I mean you do, you associate, so they form the set of partitions form a lattice under, so this is one of the operations you can do a meet and join. Yeah, so, and then you have a Mobius function corresponding to that lattice, and yeah, you try to show that, yeah, so rank arguments based on Mobius analysis. Yeah. Good. So finally, what you're waiting for, randomized communication complexity. Okay. So in the remaining time, I would like to tell you about randomized communication complexity. So here, the setting perhaps is the same, just specialized to 0, 1 to the power n, but it can be an arbitrary set here. Y's inputs can come from a set script y, and they need to compute a function. But there is an additional sort of advantage that Alice and Bob have. They have access to a shared random string. Okay. So assume that somebody has tossed some coins uniformly, R of them, and the outcome of those R coin tosses are provided to both Alice and Bob. Okay. And now Alice has some input, Bob has some input. The original input X and Y, in addition, the random string that they have been given, the same common random string has been given to both of them. And now they continue with their protocol as before, and they come to an answer. And what we require, so of course since their behavior is random, the answer that they come up with is not necessary to be the same in all instances. We require that with high probability, they must come up with the correct answer. And this is the model of randomized communication complexity. And we would now like to show that even with randomization, Alice and Bob need a lot of communication for certain problems. Okay. And showing lower bounds when randomization is allowed and a small probability of error is allowed, it's typically a harder business. Okay. And there are many techniques. I'll talk about some of them perhaps. But maybe just, does randomization help at all? The equality function. Yeah. So you remember the equality function, n bits, and they need to check whether they are equal. The equality function requires n bits of communication, yeah, no matter what they do, if they are deterministic. But the equality function has a randomized protocol with just log n bits of communication. Yeah, so if you've not seen this, this might come as a surprise to you. But yeah, so it's, randomization can do things for us which yeah, deterministically are hard. So, was there a question? So again, I'll just make some general statements and then get to something concrete. So how do you show a lower bound for randomized computing? So this is a standard principle in randomized algorithms in general, that if you can show that there is a distribution on inputs, okay, so I should probably have emphasized before, that when we are talking about deterministic communication complexity, we were talking about worst case communication. Yeah? Now, in this setting, if you want to show that the communication complexity, the randomized communication complexity for a problem is high, you come up with a distribution on inputs, a joint distribution on inputs of Alice and Bob, and show that for that distribution, no deterministic protocol can do very well. Meaning, if a deterministic protocol tries to get to the answer with a small amount of communication, then it must necessarily be making errors with high probability. High probability with respect to the distribution you have designed. Okay? So you have to come up with a hard distribution which causes every deterministic algorithm to fail with high probability. And in many cases, you can come up with such distributions and show that the randomized communication complexity is high. But not all problems, you know, are amenable to such a method. And one would have wondered if there is a version of log rank conjecture for randomized computing. And it was, never, I think, thought of as a serious method for showing randomized lower bounds. But there was an important result a few years ago where Chattopadhyay, Mande, and Sharif, they showed that the log rank conjecture is actually false for randomized computing. Okay, so there are other methods, among them about maybe 20 years ago. Amit is here. So Amit and his co-authors, they invented this method called information cost. And again, it has been a very influential method for showing lower bounds, not only in this model, but many other models related to communication complexity. So there are some iconic problems in randomized communication complexity for which we know how to show lower bounds. And those already have applications for graph communication complexity. So I just want to list a few of them and show you how graph lower bounds can be derived from them. So one of them is the index function problem. So we can read this later. The point is, Alice has a string of length n. Now Bob has just a number in the range 1 to n. So Alice has n bits, Bob has log n bits. And Bob needs to know what is stored in the ith location of x. But the trouble is, so if Bob could communicate first, Bob could tell Alice what index he has, and Alice would just send that bit. So with log n bits of communication, everything would be done. But what about the other side? Suppose Alice has to communicate first. And randomization is allowed. Could she sample something? Could she send out some parities of her bits to Bob so that with fewer than n bits, Bob would still know with high probability what this bit is. They, in the end, want only one bit of, the answer is only one bit. But nevertheless, if only one message is allowed and the error probability has to be low, then Alice must send a linear number of bits. Even though Bob wants to know only one bit, Alice has to send the whole thing. That is because Alice doesn't know which bit Bob needs. And I don't know. The Ramayana, Hanuman did not know which particular thing he needed, so he carried the whole Dronagiri, some mountain. Sorry? Oh, so he took the whole mountain. So Alice has to send the whole mountain to Hanuman. Good. So now it turns out that if Alice and Bob now have graphs instead of strings, and they would like to know if the graph has a perfect match, or has a perfect matching, that problem is hard. So Alice has to send just one message, and Bob then should know whether the graph built out of the edges that Alice has and the one that Bob has, whether the union has a perfect match. And we will show that problem with randomized communication, but with one message, requires omega n squared bits of communication. And this is a result of Feigenbaum, McGregor, Sun, and Zhang, Sharnik showed me this reduction. So here's what we do. So Alice has some n squared bits, yeah, but she thinks of her n squared bits as the n squared representing the n squared potential edges of this graph. So she takes her n squared bits and arranges them as a n cross n matrix. Yeah. So I'm trying to show that if you can solve this matching problem, then you can solve the index function problem. And since the index function problem on n squared bits requires n squared communication, yeah, this problem must also require n squared. That's where I'm going. So first, Alice's inputs are represented by this matrix where the ijth edge is placed if the ijth bit of the matrix that Alice has built out of her string has a 1. Okay. Otherwise, no edge is placed. Now Bob wants to know if I is connected to j in Alice's graph. So he builds this instance. So he takes these, there are n vertices here, n vertices here, n minus 1 vertices here, n minus 1 vertices here. And if I've done it right, leaves out j and places a matching. And leaves out I here and places a matching. There are n minus 1 vertices here. They are matched to these remaining n minus 1 vertices. Now, if the ij edge is present in Alice's graph, when we put the two graph here, we have these green edges plus one red edge, and we've got a perfect match. Now, I'll let you think about if this ij edge is not present. Yeah, so if you have a perfect matching, you have a perfect matching, you have a matching of size n plus n minus 1. Yes, that is 2n minus 1. But suppose the ijth edge is not present, the edge ij is not present in Alice's graph, then this graph cannot have a perfect matching. And why? Yeah, the good old method, how do we prove that a graph doesn't have a perfect matching? Show that it has a small cover. Yes. And do you see a cover of size 2n minus 2? Well, take all vertices except I think here, take all vertices except j here. They are touching all the edges because the only edge ij is missing from Alice's graph. Anyway, I probably didn't say it very clearly, but you understand. So what is the end result? That if you could solve the maximum matching problem, so sorry, you want to show me the card. So if so if we have an efficient communication protocol for the matching problem, then we would have one for the index function problem. And since the index function problem is hard, this problem is hard. So there are a few other problems. So this is a kind of, sorry for the typo, I didn't have time to correct it. So this is like the index function problem, but it has multiple layers. Yeah. So there is an initial vertex which is with Alice, then a whole layer of edges. Yeah. The initial edge is with Alice, the edges going out of the first layer are with Bob, the edges going with out of this A. These are with Alice, these edges are with Bob, and so on. So this is called pointer chasing in the literature. Now, if Alice starts the communication, so Alice has V0, she would tell Bob V1, how many bits? Log n bits. And then Bob would tell Alice V2, and with k rounds of communication, they would get to know the identity of VK. But suppose we just change this. We say Alice doesn't get to start, it is Bob who has to start. Now, Bob has at this point all his pointers going from the layers where he has control. But he doesn't quite know where V0 is pointing. Okay. Some version of the pointer chasing problem, similar, of the index function problem. And it turns out that if we force Bob to communicate first, but allow only the same number of k rounds of communication, then what was k log n now jumps to linear. Okay. It's slightly more than linear, but let's live with linear. Okay. So this is an important principle in random, and this can be shown even in the presence of randomization. So this is an important principle in randomized communication complexity, and this can be leveraged, or this sort of ideas can be leveraged to show lower bounds for many problems. So maybe I'll just skip this for the moment. So it turns out that in the streaming model, ideas similar to this can be used to show that checking whether the distance between any two vertices is less than or equal to 2p plus 1 in just p rounds, p passes over the input, takes superlinear amounts of communication, and ideas similar to pointer chasing are involved in that. So so two more problems that ought to always be mentioned when randomized communication complexity is mentioned. So this is the inner product function. So Alice has x, Bob has y, and they need to compute the inner product mod 2. So xi, yi, they multiply and they sum, but the sum is mod 2. So is there an even number of places, or odd number of places where they both have ones? So now it turns out that any randomized protocol, no matter how many rounds, requires linear amounts of communication for this problem. And there is what might appear to be a cousin of this problem, which is disjointness, where you do xi, yi instead of putting an XOR in front, because this summation is just putting an XOR, you put an OR. Okay? And then it is called this is probably the intersection problem. If there is even one place where both x and y have 1, then the output will be 1. So this is also a hard problem for randomized computation. If I replace these ANDs by XORs, so if these ANDs were replaced by XORs, then I'm asking, is there even one place where Alice's input is different from Bob's input? But that's the equality problem. And for that, the randomized communication complexity is log n. Okay, so it's kind of very delicate. What gates you put where is a delicate matter. So
Linear is that treatment that you talked about at the beginning, like looking at the entire matrix. Are there sort of, you mentioned that the log-rank doesn't hold, but
so there are bounds. So if you can show that again, a distribution of the inputs and no large rectangle, no large rectangle can be predominantly one time. So such a consideration can be used to show lower bounds. And there is a proof of disjointness which is based on that. So I want to just show you that the connectivity problem. So we will use disjointness, and we will show that the connectivity problem requires a lot of communication. Okay. So how do we reduce disjointness to connectivity? So let me just do some manipulation. So you remember that the disjointness problem was a circuit like this, with the Alice's inputs and Bob's inputs at the bottom. There was an OR and AND. This was the set intersection problem. That is it the case that there is one place where they both have a 1? Now, if you do some De Morgan's laws, so you put a negation on top and kind of, to compensate for it, negate all the variables here, and this OR turns into an AND, and this AND turns into an OR. Okay, put a NOT and just push it down. So now this looks like an and of ORs, and yeah, people of my vintage remember that in Russian literature, they had another model for circuit complexity called contact networks. Okay. So any network of OR and can be converted into a graph, because OR corresponds to parallel and corresponds to series. Yeah. So this OR is parallel between. Now, if there is even one place where both Alice and Bob have 1, then the graph will be disconnected. And at every place, either Alice, yeah, or Bob, sorry, saying it wrong, yeah, otherwise the graph will be connected. Yeah. So basically, using this device, and if somebody is ready to tell me about connectivity, I can use it to solve the disjointness problem. And since the disjointness problem is hard, the connectivity problem is hard. So this shows that connectivity problem needs n bits of communication. But we saw the protocol which we had initially, even the deterministic protocol, used n log n bits of communication. So actually, how many bits does connectivity need? Yeah. So for one round, yeah, you can probably have an n log n lower bound easily. Well, that was the result of Sun and Woodruff from 2015. Recently, Rakesh Venkat Chaitanya, I don't know if he will be giving a talk on that later in the workshop. We have managed to extend it to 2 rounds of communication. So you need n log n bits for connectivity even with 2 rounds of communication. So in the end, this disjointness is, that goes via pointer chasing. All right, so that's all I have to say. But once when I was giving a talk on disjointness and trying to describe the information theoretic method for the lower bound. Now, the lower bound is remarkable. It somehow shows that if you could solve disjointness easily, then you could solve AND easily in some information sense. And somehow AND was very hard to, just AND of 1 bit was somehow very hard to solve in that model. And after I described the proof at the end of the talk, Professor Vivek Borkar, a former member of this department, he came to me and gave me a slip of paper, and it said this. Yeah. So I'll stop my talk here. Thank you. So the actual practitioners of graph algorithms and communication complexity of graph algorithms will be in front of you throughout this workshop. So I hope they will be able to give you modern aspects of this. I hope this gave you some sort of an introduction to communication complexity. So if there are questions, I'll try to answer. Yeah.
So is the conjecture that the correct answer is n log n?
The conjecture is sorry, can you keep that away from me? Yeah. So yeah. So the conjecture is that n log n is a lower bound for connectivity, no matter how many rounds. And at the moment, I believe we have n log n for just 1 round of communication and 2 rounds of communication. And I think for any constant number of rounds of communication, you have a superlinear lower bound. Okay. Question?
It was talked about here that a pooling set of size k would imply a submatrix of an identity submatrix of size k.
Yeah.
I don't see how that follows.
Oh, it doesn't follow.
I see that maybe submatrix of rank k might follow,
Uh-huh.
but identity will not be followed.
Where will be lower triangle levels?
It could be lower triangle. Yeah. Maybe, sorry, I was probably a little hasty. So, yeah. No, it need not be lower triangle. So I take it back. Yeah, what I said. Yeah, I'm not sure anymore. Because in some it would be lower, some it could be upper. I don't think we have a consistent way of making it an identity.
There is a proof that you can get like half of it.
Yeah, it's possible, but yeah, I should take it back. Sorry, I was hasty. Yeah.
There any other questions? Let's thank the professor once again.
She asked him. It's my pleasure to introduce Dr. Sagnet Mukhopadhyay. He's a faculty at University of Birmingham, before which he was a faculty at University of Sheffield. He has been a postdoctoral fellow at University of Copenhagen, KTH Royal Institute of Technology, and Charles University, and he did his PhD in TIFR Mumbai. In the previous session, we got introduced to communication complexity and we saw some lower bounds. In this session, he'll be showing us how to use this technique in the context of graph problems. We are extremely delighted to have you here, sir. And the stage is all yours. Thank you.
I think I'm audible until the end of the. Cool. Okay, so pleasure to be here, and it's a tough act to follow, especially after the very person who taught me communication complexity. All right, so I'm going to talk about. I'm going to continue what Giacomo was talking about, but my focus is only going to be exclusively towards communication upper bounds. We are going to design a few two-party communication protocols, and also I must say that I'm donning two hats over here. One is the organizer, one is the speaker, and one of them will go well. So it's in your best interest to ask for this. I don't know which one you want to get ask for. Okay, so this is the plan of the session. As I said, I'm going to talk about communication upper bounds, and I'm going to focus on three problems. One is edge connectivity. The second one is bipartite matching, maximum matching. And the last one is vertex connectivity. So I have chosen these three problems to show you some techniques that we use to come up with good communication protocols. And for example, for edge connectivity, I will only focus on the approximate version of it, and I'm going to introduce the notion of cut sparsifier. And many of you already know these things, and I won't pretend that there are people who are over here who knows about cut sparsifier much more than I do. So bipartite matching would be to show you how linear programming can be used to come up with good communication protocols. And for vertex connectivity, I will point towards the linear sketching. Okay? And again, at any point, if you have any questions, please feel free to stop. I'm happy to answer. Okay. So let's start with edge connectivity. So the problem that we are going to deal with is the minimum cut problem, which is a version of edge connectivity. And I'm particularly interested in the global minimum cut problem today. So with is essentially cuts of a graph. So I've drawn a weighted graph over here where the edges has weights, but I'm mostly going to talk about simple graphs, unweighted and no parallel edges. So the cut is essentially a set of edges whose removal disconnects the graph G, and a min cut, which I will denote as lambda, is a cut with the minimum total edge weight. In the absence of weight, we're going to look at the cut with the minimum number of total edges. So, and our goal is to find a minimum cut of the graph. And as I mentioned, I'm going to talk about approximation. And I'm also going to talk about how one can take this approximation algorithm and convert it to the exact version of the problem. But the details of that algorithm, I would imagine, so Danupon will talk about it, so I will skip that. What we are going to talk about usually for approximation is a structure of the graph or a subgraph, which we call as cut sparsifier. Essentially what it does is that it subsamples from the given graph, and it also maintains the fact that the value of every cut in your subsample graph remains very close to the actual value of the cut. So it says that for any cut C, S and S complement. So S is a set of vertices and S complement is the complement set of vertices that uniquely find as G, S, S complement is within 1 plus minus epsilon of G tilde of S, S complement. G tilde is a graph which you sample. And the other thing we want from this structure is that the size of the sample graph should not be too large. Now, if we can somehow do this, then one obvious communication protocol would be for Alice to compute this cut sparsifier for her part of the graph, send that across to Bob, and then Bob adds on top of it his cut sparsifier or even the full graph that he has, and then computes the approximate minimum cut. So that's essentially the idea that we are going to develop a little bit more on this stuff. So yes.
Is this are we computing the value or are we computing the actual cut?
We are computing just the value for now. It's a value version. It's good. Yes. It will also give you the partition. So if you are looking at the version of the problem where Alice knows which edges that she has will be a part of the cut and Bob knows, that can also be worked on. Good. So let's look at a very simple sampling procedure. This is an old result of Karger, and it's a uniform sampling procedure where you sample every edge with the same probability p. And whenever so for every edge you toss a coin, which is a biased with probability p, and whenever it comes up as a head, you keep that edge in your sparsifier, otherwise you throw it away. And whenever you keep that edge, you also assign the edge weight to be the inverse of the probability by which you sampled. So, and the p, the probability, is something like 1 over lambda. So forget about the c, that's a constant, and the log n and epsilon, these are for making the concentration bounds work. But essentially the idea is that it's 1 over lambda. And if you do that, you can immediately see that the number of edges that you will sample is going to be the number of edges you start with, that's m, divided by lambda. And again, you don't have to worry about log n in these talks. I know for connectivity log n is an important parameter, but just for this talk you don't have to worry about it. Now, that what I mentioned to you, m over lambda, that's on expectation, the number of edges that you will sample in your sparsifier. And sometimes in these talks I will only talk about expected value, and you can apply some concentration bound on top of it. And sometimes you won't be able to apply concentration bound immediately, and I will mention that where that problem appears. And so this number 2 is okay. Number 1, where it says that it maintains the value of the cut up to an approximate factor, this is easy to argue again for a fixed cut. The expected value of the cut remains the same, right? Because if a cut has c edges, you sample p fraction of it. So c times p edges on expectation you will sample, and you will again increase the value of each edge with 1 over p. So c times p times 1 over p remains c. So on expectation, the value remains unchanged. So one would assume that you can just apply a concentration bound on top of it. The problem happens is because there are way too many cuts in the graph. So it's exponential number of cuts. So if you want to do concentration bound like Chernoff, it becomes a little bit unwieldy. So that's where this neat trick of Karger comes in, where it shows that you don't do it over all the cuts, you do it over cuts of similar size. And there is a really nice result of Karger which shows that the number of cuts of size, let's say alpha times lambda, lambda being the minimum cut, is polynomially bounded by n to the order alpha. So if you go over like similar size cuts, you can keep on using your concentration bound, and then at the end you just combine all of it. So that's great, it works. Issue is this number. We would ideally like to have a communication protocol which is order tilde n, so n polylog n bits. Now, if m, the number of edges that you start with, is really large, let's say close to n squared, so it's a very dense graph, then this is like n squared over lambda. And if you're, also your min cut is small, then you are not reducing the size of the sparsifier So as a running example, you can think of it as like 2 clicks connected with just one edge in the middle. So the min cut is just 1, but the graph is very dense. So you will still be left with almost n square many edges in that graph. So how do we get around this? Now that the example that I mentioned to you, it actually gives us some idea as to what to do at this point. And we will do some sort of non-uniform sampling, and I will explain this a little bit more details in the next 2 slides. So what we do is we sample every edge with a probability which is unique to that edge. Not unique, but the probability will be different for different edges. And how do I make sure that I sample edges that are important and that are so we define the notion of something called a strength of an edge. I will go into that again. Right. So notice the probability of sampling has changed from P to PE, and now instead of lambda, it is inversely proportional to something called KE. And I will define what is KE. Otherwise, the whole sampling procedure remains the same. And my claim is that we still maintain number 1, which was the main requirement for a cut Sparsifier, and the number of edges is now more manageable. It's n log n. So if the number of edges is n log n, now if Alice sends across a Sparsifier to Bob, the communication has gone down to n polylog n. So we are okay at this point. Now, what is that KE? The idea of coming up with this notion is a simple observation that if you think of this dumbbell graph, which is 2 clicks connected with an edge, you should sample the connection, the middle of the dumbbell, that singular edge, with way more probability. I mean, this should be there in your sample graph. But the edges that are in the click, you can choose not to include all of them, right? So, so what is intuitively the property of that singleton edge is that it is an important edge, and how do I define the importantness of the edge is by something called strength of an edge. Okay, so what is the strength of an edge? So strength of an edge, the definition is that we will call a connected component a K strong component if it is a K connected subgraph of the original graph. It also has to be maximal. So another way to think about it is that so this is a graph that we started off with, and this is, let's say there's a unique min cut over here, and let's say the value of the min cut is, let's say, 10. If you remove these 10 edges from this graph and look at the connected components now that is there, the min cut of those connected components should be higher, right? So they are more connected than the whole graph. Now, trivially, if the whole graph G is just a lambda strong connected component, right? So the strength of an edge E is defined to be, you look at E and you look at the, you try to look at smaller and smaller subgraphs that E belongs to, with the intention that you are choosing the smaller subgraph in order to make this subgraph more connected. And the highest value of the connectedness that you get, K prime, is going to be your strength of an edge. Yeah? Is that idea clear? So, just
for analysis, you can't, I mean, even if the graph is between Alice and
good. No. So this is what, everything is going to happen on the Alice's part. So Alice has full information about her graph, so she can compute all this strength of an edge. But you're right, in most of the models that we are interested in, this is not easy to compute, so we have to come up with an algorithm to compute it efficiently. Right. So, I mean, yes.
So just to follow up on that question, the KE value that you associate with an edge analysis graph
Yeah.
would be very different from the
Actual KE value. Absolutely, you're right. But the good thing about this cut Sparsifier is that they are sort of linear. You can take a cut Sparsifier and add another Bob's cut Sparsifier, add it on the top of it, it will remain a cut Sparsifier. Okay. Now, this strength has, it's an active, this is a very nice area of research, how to analyze the strength. And if you think a little bit on it, you will see that the way it works is that the whole graph is lambda strong. And then if you go into subgraphs, it breaks up into finer regions of stronger components. That's how it works. So our algorithm is going to be sampling edges inversely proportional to its strength. Now, we have to show this, whether they are maintained. Let's start with the easier part, which is like, can we now have a better bound on the size of the Sparsifier? And again, as before, I'm only going to argue at this point on expected value of the size, and you can do some concentration bound on top of it. So we are going to show this, and if you think about it, this is the expected value of individual edges contribution to the size of the Sparsifier. Right? You're summing it over all edges, and you're summing up 1 over KE, which is the expected contribution. And we're going to show that this is at most n minus 1, so the expected value of the Sparsifier remains n minus 1. How do I show this? Okay. To show that, we are going to look at this. We are going to look at the left-hand side of this equation, the contribution in a bit different way, but all that very natural. So we are going to find a min cut of the graph, and we are going to see how much those edges will contribute to the sum. So, well, the min cut, it's a reason why it's a min cut. It's the weakest of the whole graph, right? So the total contribution of all the min cut edges will be bounded by 1. Right? So it's 1 over KE for every edge, or 1 over lambda for every edge, but there are only lambda many edges. So 1 over lambda times lambda stays 1, right? Now, that's good. So what we're going to do, we're going to remove these edges and recurse on 2 sides. Again, we're going to find out on the resulting components, add up their contribution of those edges and keep on doing this. Every time we are adding 1, and whenever we remove a set of min cut edges, we are increasing the number of components by 1. So this whole recursive procedure can only go for n steps. Every time you go add 1, so you have a bound which is n. So if you be careful, you will get the n minus 1 as well. Does that make sense?
You repeat this argument, like why is it for a min cut? If you look at the strongly penetrate component, not the min.
So this is the original graph. Let's start with the first, the original graph.
Right.
The strength of every edge in the min cut is lambda.
Right.
Because what is the strength? The definition of the strength is the, so this edge is the min cut, means that in the whole, the graph, the component that you are considering now is the whole graph. Right? In any smaller graph, it cannot be a stronger component. That's the definition of the min cut. If you, yeah? If you are willing to believe that, then it is sums up. Good, so that's the size part. I will now just give you what would be the problem in the approximation part. I won't go into detail because it requires a full lecture on how to prove this. But here is the problem. Previously, what I mentioned when I went for uniform sampling, I just said that, you look at the expected value and then you apply some concentration bound on it. And even then we had a problem because there are way too many cuts, and you have to you have to work with the concentration bound in a much more careful way by using Kargar's argument. But now we have an added problem because we are sampling things with different probabilities, right? So we have to do some more tricks at this point. So the I mean, the trick is pretty obvious if you think about it. What you are going to do is that you're going to bucket the edges which will be sampled with similar probabilities. Look at only those edges and you run this normal uniform sampling bound on it, and at the end combine all of them. But it's easier said than done. You have to be careful there. So, which is why I'm not going into it. But again, it's a good place to look at it is to look at not the Benzukarger paper, but lecture notes after that came out of his. Good. So, if I have that, then I should mention over here, this is one way of doing things. There are multiple other ways of doing these things, again by sampling. Here I have sampled with strength, inversely proportional to strength. You can also sample inversely proportional to the effective resistance of an edge, and that takes you to the area of spectral sparsification, which is also extremely interesting, and it's still an active research area. For example, Sanjeev has a very recent paper where he looks at your graph, which I have guaranteed you to be a spectral sparsifier. Now, can you come up with the original graph for which this is a spectral sparsifier? So, all this is to say that this is an active area of research.
Even if they are independent, right? So you can't use like a Zuma or like some.
You can. Then you have to sacrifice on the union bound.
Is it because you want a multiplicative guarantee that's the difficulty, or?
That's usually, if you want the multiplicative guarantee, then the assume of whole thing would be a little bit problematic to work with. But I'm not sure it might still work. I haven't worked it out. Okay, so that's all about the sparsifier, the approximation version. I will just give you a few pointers as to how to go from here to the exact version of the problem where you want to know the exact min cut of the graph. And just
So for the approximate version, are you saying Alice and Bob are both going? Alice is going to sparsify her graph and send over the sparsified graph to Bob.
Yeah.
Who will then compute?
Yeah. Exactly.
So how do we compute this K value?
So Alice has. So this is another thing about communication complexity. We assume that Alice has unbounded computational power. And because she has unbounded computational power, she has all the edges that she has, and so you can do it. But there are better ways of, like more algorithmic way of doing KV values. Good. Okay. So, wow. Yeah. I'm going to give you a 2 or 3 slides based on how to go from here to the exact. And again, I would very much appreciate if you look at you listen to Danupon's talk where he's possibly going to talk about this. So how to go from here to exact, you reduce the problem to something called a 2 respecting min cut. And this is a famous framework by David Karger again, where he looks at this problem, which is a min cut problem, but with a bit of constraint, which comes in the form of a spanning tree of the graph. So you have the graph, you're also given a spanning tree, and you have to come up with a minimum cut which 2 respects that spanning tree. What do I mean by that? A cut 2 respects a spanning tree means that it cuts at most 2 edges from that spanning tree. Okay. So for example, this is not a 2 respecting cut. If you think of these fat edges as the spanning 3 edges, because this cuts 3 of them. But this one, the previous one is this is a 2 respecting cut. Now, the theorem of Karger says that efficient algorithm for solving 2 respecting min cut implies an efficient algorithm for solving the actual min cut. But to have this reduction, you need to have some idea as to what the min cut is, some approximation of it, because you have to go through some process called tree packing. And to know that, you need to have an approximation value of the min cut. You run the first algorithm, Sparsification, and then from there, on top of that, you run the 2 respecting cut algorithm. I will not go into much details. Good? So far? Now let me move on to the next problem. Oh, I will skip this. This is just to show you that just this algorithm will give you algorithms in different models of computations, but in the interest of time, let me skip ahead and go to the next interesting problem. Yes?
So how does the two respecting cut help here?
Sorry?
Like how do you use the two respecting cut here?
So again, the setup is the same. It's like Alice has some edges, Bob has some other edges, and they both know of a spanning tree of the graph. And now they have to find a min cut which respects that spanning tree.
Okay.
Okay. Okay, let's go into the another interesting, well-known problem, which is the bipartite matching problem. So again, this is just going to be a snapshot of different areas or on different results that has appeared in the last, let's say, 5 to 6 years. So we are looking at max cardinality bipartite matching. So we are not working with weighted graphs again. So the input is again a bipartite graph with the left vertices and right vertices and edges between them. And you have to come up with the maximum matching. And most of you are already familiar with this linear program, which says that I have a variable for every edge, and I want to maximize the sum over these variables with the constraint that if you look at a vertex V, the number of variables, number of edge variables that fires, the total contribution of those variables is bounded by 1. So if these variables are indeed 0, 1, then of course only one edge can fire. So you get a matching. Of course, as usual, you look at the relaxed version of this problem where you relax the constraint from the variables being 0 or 1 to some number between 0 and 1, and by some amazing theorem of total unimodularity, it will tell you that both will give you the same values. Okay, so this is the thing that we are going to work with, so linear program. Now, again, the setup was, for the communication protocol, Alice has some edges, Bob has some edges. So in the linear programming formulation, how does the setup look like then? For that, we will go to the dual of this problem, which is the vertex cover. And Giacomo also mentioned. So the vertex cover is essentially you have a variable for every vertex, xv, and essentially you want to have the minimum number of variables which covers all the edges. The way you show that is you look at for every edge whether the contribution of the two endpoints of that edge is at least 1 or not. Again, this is, most of you are familiar with this, right? And by LP duality, it shows that if it has a vertex cover of size f, it means that the maximum matching is also of size f. Now, we will change this search problem to a decision problem. We will show that our goal is to find if the minimum vertex cover is of size f or not, for now. Again, and I will tell you why I'm looking at vertex cover at this point. You see, let me go back to this slide itself. If you look at Alice and Bob's input, they have edges, right? Here it means that they have constraints distributed amongst them. So every edge has a constraint. So you can think of this as a linear program. The constraints are distributed between Alice and Bob, and they want to find out the feasibility of the problem. And I will come to the feasibility part of it. Yes?
So these constraints, can there be overlaps?
What do you mean?
Overlaps. So a certain set of constraints is given to Alice.
Yeah, for now, the setup that we are looking at, Alice's set of edges are disjoint from Bob's set of edges. Right, so we are looking at the feasibility version of the problem where we are looking at xv, the vertex cover is of size at most f or not. Yeah? And I have put in 1/3 over here. It will come in handy later on. But you see that if I put a 1/3 over here, it doesn't really change the feasibility problem, because the value of f increases by 1, and you're putting a 1/3 additional, so it remains the same. And this essentially is now a communication complexity of a linear a linear system. And this is a fairly new area of research. By fairly new, I mean, let's say 5 years. Yeah. And as a good place to start is an amazing paper by Santosh, Bala, Wang, and Woodruff. It appears in Soda, where they look at a general linear programming system and try to look at the communication complexity of it and give tight bounds over there. But for us, we are looking at a very specific linear program. Can we do something better over here? And the answer is actually yes. So this is what you're going to do. This is how the protocol works. So this constraint is known to both Alice and Bob. So you look at the whole input space, and you cut it, and you look at the polytope, which is only satisfying this constraint. Okay. Now, no other constraint is present at this point. We are going to put the constraints one by one. Alice and Bob will do that. And for that, they will do something called a cutting plane method, which is the following algorithm. They look at the polytope that is they're working with right now. They compute something called the center of gravity of that polytope, which is essentially an expected value. It's an average of all the extremal points of the polytope. And then they will check whether this center of gravity is a valid solution to all the constraints or not. Note that to start off with, both Alice and Bob has a full polytope with them. And we will make sure that every point in time in this communication protocol, they know the full polytope. Is that the constraints are distributed. So they can compute the center of gravity, and individually they can figure out whether some constraint or edges are violating that center of gravity or not. And if that happens, they will exchange that edge and again update the polytope. So the first is the center of gravity here. Well, this constraint violates that. So you look at, you update your polytope to this side, compute the second center of gravity over here, and keep on doing it. And there is this amazing theorem from 60s which says that if you do this process, every time you cut it down the polytope, it cuts down by a constant factor. Okay? Now, so that's the, so if it cuts down by a constant factor, where will it stop? Because this is a huge space, so you need to have some stopping condition. So the stopping condition is when your polytope becomes as small as this. And yes?
So what is being assumed about the LP to say that the cutting plane cuts down a constant factor?
It's nothing about this. If you look at the interior point method, if you consider the center of gravity and cut it down with any hyperplane that is crossing to the center of gravity.
Okay.
Okay. Okay. So this is my stopping condition. This is a manufactured stopping condition, and the way we manufacture this by putting this 1/3. What it says intuitively is the following: if you have a point in your polytope which is feasible, putting this 1/3 will put a ball of some radius on top of it, which all are feasible, and that will let you have a bound on, like if you keep on cutting, and if your size of the remaining polytope goes below the size of the ball, rest assured that there cannot be any feasible points. So you start with size 1, you stop here every time you cut down a constant factor. So the communication the number of rounds is only n log n. If you put a log, you will figure out that's n log n. And every round, Alice and Bob has to exchange one violating constraint, so that's an edge. So that's log n bits of communication. So you get n log square in communication.
By size you mean volume?
Sorry, volume. That's my bad. Good. Now, this is a search problem as it is. I'm just saying that the vertex cover is of certain size or not. So it in turns gives you the size of the maximum matching. The question to be had whether can you actually find the maximum matching? And the answer is a resounding yes. If you look at the edges that actually are violating, which both Alice and Bob knows, a maximum matching is hidden there. Okay. Again, it requires some amount of calculation, some amount of thought to figure that out. But yeah, this is there. So it's both a search, the value version of the problem and the search version of the problem. Both has n polylog n communication complexity. Is that clear up to this point? I mean, it need not be extremely clear, but just to have an idea of what is happening with the techniques that are involved. Okay. Again, so this is another slide I prepared just to show you that this simple protocol will give you optimal bound in many, many other models, quantum H query or QAV and all of these things, but I will not go into this at this point. But just like MinCut, this communication protocol, once you have it, it will give you optimal protocol for many other models. And that is sort of like a recurring theme. And the reason being, as Giacomo said, the communication protocol, the reason why communication protocol is so useful to complexity theorists is that it captures the core hardness of the problem. So if you can think of it as like if you can solve the core hardness of the problem via communication complexity, the other things will take care of itself. You know, it's not obvious always the case. For example, you also assume that Alice and Bob has unbounded computational power. So how do you even, if I now have to do this problem in other models, you have to somehow figure out what Alice and Bob are doing and try to make them more algorithmic. And for certain problems, we have seen that you can do it. For example, for MinCut, you can do it. For Vertex connectivity, also you can do it. For bipartite matching, however, the rub is that Alice and Bob, in their own world, are computing the center of gravity, which is a very hard task. And so we don't quite know how to use this protocol to come up with, let's say, a good unit cost RAM or like a sequential algorithm. But in whichever model where you get this, internal computation to be free, this protocol seems to be okay at this point, yes.
So, but you can approximate the centroid?
Yes, we can approximate the centroid, but I think, and this is a few years back now, so I remember, if you work with the approximate centroid, you might get an approximate maximum matching, not the exact. It's hard to convert it to an exact version of the problem.
You run the ellipsoid instead.
Sorry?
Instead of the centroid, maybe you can run the ellipsoid.
You can. Sorry.
So why not ellipsoid?
Why not ellipsoid? I mean, sure. I mean, it's a good starting point. I mean, I don't know at this point, to be very honest.
I mean, if I understand, you're getting this separation. Yeah, basically,
Yeah. Yeah. I mean, absolutely. I mean, if you can come up with a more, reasonable way of coming up with this center of gravity or whatever, which cuts down like half of it, and if you have dare I say, a more polynomial time way of doing things, then it will immediately gives you a maximum matching algorithm which is sequentially great. However, to come up with a maximum matching algorithm which is sequentially great, in the sense linear runtime, is a hard problem. So you have to be careful there. All that we know is that you can solve it in m, the number of edges to the power 1 plus little o of 1, which comes from the recent max flow breakthrough. Sanjeev has a paper which combinatorial, which goes to n square, n to the power 2 minus little o of 1. Is that right? 2 minus little o of 1.
2 plus
Oh, so 2 plus little 1. Yeah, but we do not know anything better than that. So yeah, I mean, we would like to see something like that works out. Yes?
So I think Giacomo showed that one round you need n square.
Correct.
This is n.
Yes. we need n log n rounds, yes. And no, not need, in the sense is like this algorithm uses n log n round, and to come up with any trade-off is an open question.
So even 2 rounds is the lower bound.
That, I mean, not that I know of. One might come up with something. Any other question? Good. So then I will end with the last problem in the series. And just to let you know that all of these problems fall in the category of something called a submodular function minimization, which is why I'm interested in all this. And also in that submodular function category, the outstanding open question to prove any superlinear lower bound of a submodular function using submodular queries. It just shows you that these two problems you cannot hope to prove a superlinear lower bound with that. Let's come to the vertex connectivity.
Query complexity result out of communication.
That's right. And I will not go into too much details on it, but all the result that we know in the submodular query model to prove lower bounds comes via communication. And yeah. Okay, so vertex connectivity. So again, we are interested in global vertex connectivity, which means that you have to find the minimum number of vertices, not edges, now vertices, whose deletion will disconnect an undirected graph. So for example, this is a set of computers that are connected by some network, and if you drop this guy, something that happens, maybe with what I realized the LinkedIn post that's what happens with Indigo, apparently. Somebody was giving out from his local drive what are the boarding passes. Well, I'm not sure. This is being live streamed, so I should not say it. Anyway. That's we are looking for the weakest link, weakest vertex whose removal will disconnect the graph. Now, what is a trivial vertex cut? A trivial vertex cut is like you look at a vertex, a single vertex, and deletes all of its neighbors, right? It will separate out the vertex from the remaining set of vertices. So, and Alice and Bob can really do that with small communication, right? Because Alice and Bob will jointly compute the vertex which has got the minimum degree, and once they know which vertex is the minimum degree, they will just exchange the neighborhood, and that will be our minimum vertex cut, right? So we are looking at a problem where this is not the case, where the minimum vertex cut is actual minimum vertex cut is even smaller than the degree. Okay? Now, if you look at the ST version of the problem, where there is a specific S vertex and source vertex and a sink vertex, and if you want to remove a set of vertices which will disconnect S from T, that problem is equivalent to maximum bipartite matching. The reduction is not extremely straightforward, but it is there, and essentially it says that if you can solve bipartite matching with C communication, then you can also solve ST vertex connectivity with ordered C communication. So the ST version, by our previous the discussion that we did, is solved. The question is like whether the global version is solved. This sort of goes the other way for edge connectivity. For edge connectivity, the ST version is harder, not provably, but intuitively harder than the global version. And also, you do not need to solve ST in order to solve global. The Kargar's framework will give you a different way of solving it. But here, for vertex connectivity, we don't quite know. For example, like Tachapon has quite a few results where it looks at the connection between ST and the global. And there is, for the sequential model, we know that if you can solve the ST vertex connectivity quickly, you can also solve the global vertex connectivity quickly. This is a very recent result. Let's say 4 years back. The question is whether the same happens for communication complexity as well. In that case, we are done, right? So we are going to show you that that is not the case. I mean, we are not going to show you that is not the case. We are going to give you an algorithm, and in the end, we are going to show you that this is the best you can do. So, and that's the end of the story for today. So let me give you an algorithm, communication protocol, which runs in n to the power 1.5 communication, n root n. Okay, this is how it works. So we're going to talk about something. We're going to talk about small and large, and they are not, the negation of each other, just for the sake of this next 10 minutes. Okay, so the small means smaller than root n, and large means really large. It's like a constant fraction of n. Yeah? So of course, just to make matters more complicated, I'm going to talk about not small and not large. And again, not small means it's bigger than square root n, and not large means that we don't quite have a bound on the size of it. Yeah? Good. So in the previous picture, this is the notion I'm going to work with. So S, capital S, is going to be the vertex cut. If you remove it, it breaks down into two parts. One is the left part, one is the right part. So if this is the situation in your graph, where you have a large L and a large R, yeah, what can you do? In this case, the problem becomes pretty simple. You just sample a bunch of vertices from the graph. With high probability, somebody will land in L. With high probability, somebody will land in R. And for every pair, you run the ST version of the problem. And if you run it a few times, constant number of times, you will actually find the vertex connectivity. Okay? That's one. So it doesn't require too much communication. Order tilde n is fine. N polylog n is fine. Of course, the real life is not like that. You are not going to have large N and large R all the time. So what can you do when you don't have those? So let's work with the fact when you still have large R, but only the guarantee of L is it's not small. Okay, so it's at least square root. If we run the same algorithm, now you have to sample a bit more to hit the set L, right? So it's of size, it has size at least square root n, so you have to sample square root n many nodes to hit L, constant many to hit R, and you look at the pairs and run your ST vertex connectivity. So that will give you n to the power 1.5. So we are getting there, n to the power 1.5. Okay? So this part is still okay. But remember, we crucially use the fact that R is large over there. Because we said that if you sample a constant many vertices, it will hit R. And so, the whole communication, the sampling was dominated by sampling and trying to hit L. But if your R becomes small, then you also have to sample even more to hit R. And then the communication will blow up. So how do we deal with that? So this is a situation where you have a not large R, and without loss of generality, let's just assume that the size of R is still bigger than L, and you can remove those. What you do is the following. You again sample a set of vertices, n over L of them, which is again, if L is square root n, is a square root n many vertices. But now we are going to do some pruning. So you look at a vertex, call it an S, yeah, and you want to find its pair T. The way you're going to do that, you're going to fix this vertex and look at all other sample guys. And if you look for a vertex which is not in the neighborhood of this guy, and call that T. And the claim is that this will be enough for you to land one vertex in R. Why? Again, I will not give you the detailed proof, but this is the intuition why this is happening. Let's see if I can make any sense out of it. So, we have assumed that the actual mean vertex cut is smaller than the degree, right? That's one thing. So neighborhood of U, the size of the neighborhood of U is bigger than size of S. Okay? the second, which is n of u is at least s, the other thing is that the neighborhood of u is completely contained within L union S, right? Which means if you look at the area, so this is the yellow area is the neighborhood of u. If you look at the area in S, or the number of vertices in S, which is outside the neighborhood of u, there are not too many such vertices. How many? Actually, this is smaller than L such guys. So the probability, when you're sampling with probability 1 over L, with constant probability you will skip that area and you will land there. Yeah? So if you can, all this is to say that if you indeed has a vertex here, landing over here, with high probability that guy will be a neighbor of a vertex who you have sampled in L. So the pruning process that I told you is going to cut that off. Now, of course, you might say at this point is that what is the probability that you will even get somebody over here in this case? You might have just cut everybody off, but those things can be taken care of. Okay? But this is the general idea. So what is the communication for this? Well, you have sampled n over L vertices. For each vertex, you have to compute the intersection of u with the neighborhood of this guy. But the neighborhood is distributed between Alice and Bob. So you have to do something like a set disjointness over here. And that will require an n bits of communication. So in total, that will be n squared over L to actually find these pairs. And once you have found this pair, there are n over L many pairs. And you have to run for each pair the ST version. So that's another n squared over L. And if L is root n, you have n to the power 1.5. Okay? Okay, in the last few minutes, I'm going to talk about when things are even worse. So 2 more cases remaining, and I'm only going to skim over them. Okay. It's annoying that this is a case-by-case analysis, but I mean, I'd be happy if somebody comes up with a more coherent way of expressing this algorithm. But it is what we have right now. Actually, only one more case remaining. So, in this case, L is actually small. So the bound is root n. The upper bound is root n for L. What can we do over here? Now, here is an observation which says that if we can somehow find a vertex set V prime, which is a superset of L, and we know this information for any pair of vertices in that superset, then we are done. What is that information? You look at the neighborhood of U, you look at the neighborhood of V, and look at only the exclusive neighbors of U in that set. Okay? So the neighbors of U which are not a neighbor of V. Okay? What that actually is, let's try to make it a little bit simpler, what that means. Okay? And for that, let's see the G prime, which is computed by the ages that we learned in this process. Like, we only have the information of n of u, neighborhood of u minus neighborhood of v. We know some of the ages. We put those ages and look at the graph. Thus, we have constructed. What are the edges that are missing at this point? Well, think of an U. If it misses an edge, ux, this means that this x is a neighborhood of everybody in V prime, right? Which is why you missed. So, if we just, the only thing that are, if consider this set W, which has got vertex, which has got an edge to everybody in V prime, none of the edges will occur in your graph, in your G prime. But this W is not a function of L, it's a function of just the V prime set. So if you compute the L on this subgraph, it will still give you the correct minimizer. Okay. Again, I will not go into too much details on it, but this is just a way to show you that you can afford to miss some edges and still be okay with computing the minimum vertex cut. If that is indeed the case, for this we have a very nice structure on the neighborhood of u and neighborhood of v. We show that the Hamming distance between the neighborhood of u and neighborhood of v is always bounded by the size of L. Okay. Again, these are quite a few steps that we are going over here, but this is essentially what we want to work with. We want to work with the vertices such that every two pair has a property that if you look at the Hamming distance between the neighborhood set of these two sets is bounded by L, the size of L. Once we have this, we can use something called linear sketches, which says that if you have a vector which has got number of ones which is bounded by L, you can compress it and you can send it across, and from there you can figure out which are the places where the ones were. Okay, so this is both sketching and also recovery, sparse recovery, and this is an extremely active research field. It uses left, right, and center for all sorts of streaming, query, and all these models. That's what we're going to use, and essentially we're going to pre-compute the sketches, both Alice and Bob, and they're going to exchange between each other, and that's going to be enough. It's called linear, and that's also important, which means that if Alice is a vector and Bob as a vector, and if you add them up, and in this vector, when you add them up has a bound on the number of ones, then Alice can compute her sketch, Bob can compute his sketch, add these two up, and that will remain a valid sketch. So they're going to use that to come up with a sketch of the whole graph. So all this is, I understand, this is a pretty new result, so I wanted to show it to you. And I wanted to show it to you just because of the fact that this solves a question that we came up with, and we solved it, which says that whether ST version is enough to solve the global version. And we show that for communication, that's not true. In communication is the only model that we know at this point where the ST and the global will differ by a square root fraction. Okay? Good. So I will stop here. Happy to answer any questions if you have any.
Do we have any questions?
Quick time.
If not, let's again thank Professor
Let's do that.
Good afternoon, everyone. I'm honored to introduce our next speaker, Thachapal Saranurak. He is an assistant professor in the computer science department at University of Michigan. He specializes in designing fast and efficient graph algorithms with applications in dynamic networks, robust optimization, and large-scale computation. Dr. Saranurak is also the recipient of the prestigious Pressburger Award in 2023 and the Sloan Research Fellowship in 2025 for his contributions to theoretical computer science. Yeah, so let's welcome him.
Thank you. Yeah, great to be here, first time in India. And okay, so this talk is going to be about dynamic graph algorithm. So let me start with telling you what is dynamic graph. What is dynamic algorithm, right? So in a really high level, dynamic algorithms are algorithms that interact with the user. Right? It's not just one shot where you get input and you output and output. So here you have a user. Then the user gives some update to the input. The algorithm returns the new output, and the user might update again. And the point is that you don't want to recompute everything from scratch after each update. That's going to be too wasteful. Yeah. So just one bit of update. You should just do something, have some data structure so that you get a new output faster. Yeah. So in the context of graph, in this talk you should think like this. So you have an input graph in the beginning, let's say G0, and in the beginning you have some time to pre-process it and then get some data structure. And after that, for each time step, you can get some update. You can get some update and query. Okay? And this update and query are generated online, on the fly. Okay? You don't know what is the next update. And then the goal is to update your data structures and or answer the query. So often in this talk, actually just going to be just insertion or deletion of an edge. Sometimes we just update a vertex, but for this talk, just think like you update, add one edge, delete one edge, one at a time. And the example of it can be to answer some simple query, like is the graph remain connected, or what is the current distance between two nodes S and T. So this is just query and answer some of the query. But you can also maintain objects. For example, you want to maintain a minimum spanning tree of the whole graph under update. So this is not just some number, yes or no answer. It's just to maintain some bit objects in the graph. Okay. So this is a type of thing that we consider in this area. And here, now I will introduce some terminology that we use. So I will, after many updates, after I steps. So you start with G0, and then next update you get G1, G2, G3, G. The update sequence is just a sequence of update and query that the user gives to us. And the update time is the time that is needed for each step. Okay. So there are two types that we usually look at, two types of update time. The first is worst case update time. So we said that we have worst case update time T. If every step the data structure just require at most T time. For example, if this is an update time for each step, the worst case update time is just here. Because this is the worst case time. But amortized time, there's another notion called amortized update time. So we said that we have T amortized update time. If basically the average time is at most T, but this is average over steps. not averaging over some distribution or something randomized. This is averaging over steps. So what I mean is that after k many steps that you take is at most kt. So averaging over k, this is at most t. For example, here, if you can see from this picture, if most of the time you have update time around here, so on average, the amortized update time is around at most this much. Yeah. So amortized update time can be smaller than worst case. If you can guarantee worst case time, that's better. Okay. And then there is another one which is pre-processing time or initialization time. This is just a time to pre-process the graph G0. So which is like here, before you get any update. So this doesn't count in the update time. Okay. So that's just a standard terminology. Yeah. And ask any question if you, yeah. Yeah.
The pre-processing time still has to be polynomial input sense, right? Or will you just not assume anything?
Yeah, you can think like a pre-processing time should be polynomial time. Yeah.
Okay.
In most of the thing in this talk is just even going to be linear time. Yeah.
Okay.
Yeah. Okay. So last slides on the terminology. Okay. So fully dynamic algorithms are the ones that handle both insertion and deletion. And otherwise, if you can handle only one type of updates, then it's called partially dynamic. If it's, for example, incremental algorithm handle only insertion, decremental algorithm handle only deletions. So if you look up for the literature, this is the word that people use. Okay. So what we're gonna do in this 2 hours? Okay. What I want to tell you is like 3 templates for designing dynamic graph algorithms. So the first 2 are quite standard. It's called rebuild and batching. And then the third one, this is more modern. Okay. So all of these templates are general. It's really generic. It's applied to all problems. And not just even graph problem. The first 2 apply to any problem. So if you work on some dynamic string, dynamic geometry problem, it works too. The third one is specific to graph. And it's quite interesting, and I want to tell you because you might have seen some breakthrough in graph algorithm like fast, almost linear time max flow, and other fasting in recent years. A lot of work that enable this kind of breakthrough is dynamic data structure, and the template that they use is kind of based on Vertex Sparsifier. Okay, so the first 2 are really classical. When people say just use batching, that's like everyone knows, and I want to tell you what's that today. The third one, quite modern. Yeah. Okay.
Quick question. So you're only amortizing over the time complexity. It's other models that study that your say approximation ratio is amortized. So most of the time you're
Okay.
to approximation.
You asked about like do people study something called amortized approximation instead of amortized update time?
Yeah.
I don't know. Yeah, good question though. Yeah. Okay. So yeah, and for each of this template, I really hope you really understand it by giving you some complete proof of some concrete problem. Okay. So let's start. Okay. So the first one is like a warm up. Is template 0. Okay. So as a running example, let's look at this problem called dynamic meshing, approximate meshing. Okay. So just a reminder, a meshing is a set of vertex disjoint edge. Okay. Like this one, the edge set are disjoint, so this is a meshing. But it's not a maximum meshing because this one is larger. Like this one has size 3, this one has size 2. This is a maximum matching. And for any graph, I use mu of g to denote the size of a maximum matching. Okay, so what's the problem here? The problem is you have a graph with n vertices. And then there is an online sequence of deletion and insertion. And let's say you want to maintain approximation 1 plus epsilon of mu. We're going to see how to maintain the matching itself, but yeah, let's say we just want to maintain the size, approximate the size of maximum matching. And one trivial way to solve this, for any dynamic algorithm, one trivial way is just to compute everything from scratch after each update. So now, if you want approximation of mu, there is a known algorithm that takes linear time in m, in number of edges. So number of edges over epsilon, you can actually approximate mu. In worst case, this is n squared update time, just by recomputing everything from scratch. So let's take this as as a black box. There is some linear time algorithm to do things from scratch.
So this also works for vertex updates, right? The recomputing.
Yeah. You recompute everything from scratch. Whatever type of update you have, you can do it.
Yeah, the same random.
With the same running times. Yeah, just recompute. Yeah. And now what I will show you now is like how to improve from n squared to n. Okay. And the algorithm is going to be really simple. The algorithm is to repeat the following. First, I just rebuild. Here I mean just to get approximation of mu by computing everything from scratch. Just use a black box static algorithm. Okay. I rebuild and spend linear time. And then for the next epsilon mu steps, epsilon mu tilde steps, I just return what I have computed before. I do nothing. Like for the next this many steps, I just return what I have computed at this time. And after that, rebuild. And wait for the next this many steps, mu, epsilon mu, and repeat. So that's the algorithm. So why this is correct? Why is it okay to just wait and do nothing? So the key observation is just that if the problem is a maximum matching, the answer is quite stable. Okay? Imagine this: you have a graph, and you insert one edge. How much a maximum matching size can increase? At most 1. When you delete one edge, okay, maximum matching size can decrease, but by how much? At most 1 again. Okay? So each edge update can change the size of mu by at most 1. So it means that, okay, when you rebuild, you get this 1 plus epsilon approximation. Okay? And during the time that you wait and do nothing, you get some additive error of how much time, how many steps that you wait. So the thing that you maintain here is just always going to be 1 plus O of epsilon approximation of mu. Make sense? So this is why this algorithm is just correct. Simply because your the objective, the maximum matching, is stable under updates. Okay. So you just can manage to just wait and do nothing for some time. Okay. So correctness is fine. So now let's see why the update time is better, like not just n squared but n. Okay. So the update time, what is update time? Let's look at, like, we're just gonna analyze amortized update time. Amortized update time is what? is this much linear time in the graph size over this much time, this many steps. Okay. So this much time over this many steps. So amortized time is this. And I claim that this one is at most n. So let's prove this. So the proof is going to be just because I claim that for any graph, the number of edges in the graph is at most the size of the maximum meshing times 2n. So let's see this simple proof. Let's consider any maximum meshing in the graph, like here. This is the maximum meshing. And observe that every edge in the graph must be incident to this m star, the maximum meshing. Like this one is incident to the blue edge, this one too. Because otherwise, if there is some edge, there is not even incident to the blue edge. You can just add that and get a bigger one. So now, imagine that if you delete an edge, delete this edge from m star, okay. How many edges you will remove from the graph? It's going to be, you're going to remove, let's say this is edge uv, you're going to remove this edge too and this edge too. So you're going to remove at most degree of u plus degree of v other edges, in addition. Okay. So you're going to remove at most 2n more edges for each blue edge that you remove. So it means that if you repeat this for every blue edge, there's no edge left. So it means that like the total number of edges that you remove is at most, you remove this many times, each time you remove 2n edges at most. So you get this bound. Given this bound, it means that this one is at most n over epsilon squared. Okay. Alright, so that's a simple template. So let me recap. This template basically kind of says the following in general. Suppose that you have any algorithm A, and if it can handle L many updates, insertion, deletion, and if let's say that the review time is TB, and the worst case update time is TU, okay. Like this. Okay. You get review time and some worst case update time. Then what you can get immediately is you get another algorithm A prime that can handle infinitely many updates. And the update time is going to be TB over L plus TU, the amortized update time. Okay. So in our case, like the dynamic matching that we get n here because L here is like a epsilon mu, TB is like a number of edges, TU is 1, and by plugging this thing into this, you get n. Okay, but okay, this is a simple one that gives you amortized update time. So now let's do something a bit more non-trivial to make almost the same thing here, but now worst case, so better. It's a stronger bound now. Okay. So this is template that is people in the area just call rebuild in the background, and has been there like for many years, like 40 years at least, and also in this book by Overmars. Used in many papers that sometimes we don't even care to write, just said we just reviewed. And yeah. Okay. So recap. Okay. We have this template, right? Okay. And I just gonna from now just write something simpler. Like I just gonna write instead of update time like this. I just simplify the picture a bit. Okay. And the next goal now is we want to, given this algorithms black box, instead of getting this another algorithm, dynamic algorithm with this amortized update time, we want worst case. But I'm gonna show you something a bit weaker. That is, this algorithm is gonna be correct only on half of the update sequence, not at all time step. But we're gonna fix that quite easily. So let's do just something that correct on half of the things, half of the time first. Okay, so here's a way to do. What I'm gonna do is consider like this phase of L stack that our black box can handle the update. We're gonna separate this, divide this phase into period, into 3 periods. Okay? So this is the phase of length L. Let's say that this is like a time t0 here. Okay. And that's going to be the first phase, which is to rebuild. Previously, the rebuild time is just going to be like the first time step in the first phase. But now we're just going to kind of make it longer into L over 4 steps. So what we're going to do, we just like look at the graph at this time, the graph G0. And we're just going to rebuild the data structure for GT0. But we distribute the work evenly on this period, on the red period. So as time goes by, like we spend some time, but we just spend time to rebuild the data structure for the past. Okay. So just ignore the update. Spend some time to rebuild. But spread the work of rebuilding. The rebuild time was expensive. We just distribute this work. Yeah.
So we are unable to answer queries during this time?
We will not be able to answer the query during this time. We will fix this soon. Okay. Yeah. Yes?
So we can distribute the work. The queries are still coming with time, right?
The query might be still coming. And let's say we ignore that. I will fix that issue later. Okay. So at this time, after this time, okay, we have successfully rebuilt the data structure for the past at time t0. So now it's time to catch up. Okay. So for the next L over 4 update, what we're going to do is like given an update for one step, we will feed 2 updates to the data structure. So we double the speed. So it means what? It means that after the next L over 4 updates here, okay, at the end here, the data structure basically catch up with all the updates. And we are now ready for to answer queries. So now is the time that we spend some work and we are ready. So for the last L over 2 steps here, now is the time that we can just feed the update normally and can answer, we can get the correct answer from this period. So during the green period, here is the time that we can answer the thing correctly. And note that, okay, right now we can answer the thing correctly half the time, but at least what we gain here is that the worst case time that we spend per step is now TB over L plus TU. It used to be amortized, now worst case. So, okay. So now let's fix this issue that is correct only on half of the update sequence. Okay, let's fix this. So the idea is simple. We're going to make 2 instances of the data structure that we just shown, A''1 and A''2. And we're just going to schedule their period to interleave so that at every time step, one of them must be ready to answer. So in picture, it looks like this. The first one that we have from the previous slide looks like this. is correct here, here, here. So let's make another copy. So that now on this period that the first guys are not ready, the second one is ready. So except that like the second one should be ready from the beginning here. So in the beginning here, just spend pre-processing time on the second one, but that doesn't count on the update time. So this spend pre-processing time before seeing any update. So now, just that. It's just now correct on every update.
So your query will report from A to double prime.
Yeah, like when this guy is ready, when we feed the query, we use A double prime 1 to answer. But during this time, given this query at this time, we just use this data structure. Okay. Questions?
When you're feeding the query, what exactly is happening?
When you feed the query to like when you get an update, you feed the update to both data structure. Okay? But at any point of time, you know which one is ready to answer the query. So you feed the query to both of them too, but you just just get the answer from the one that you know is correct. Yeah.
Yeah, so your the data structure that is ready, you are giving the same answer for half of the time.
Same answer half of the time? I'm sorry, I don't quite understand.
I mean, you have to compute the maximum matching rate. So with the correct data structure, how is it? So at every time step when you get a query, is it giving the same answer, or is it actually recomputing the maximum matching again?
Okay, good. So the question is like does the data structure just does it for maximum matching problem, does the data structure just don't do anything here and here? Yes, for maximum matching. But here I'm giving a template that works for any problem. Okay. So I just said that like for any template, like for any if I'm giving you this black box for any problem, not just maximum matching, such that it can handle L updates and can reduce in this time TB and worst case time TU. Then just use this template for any problem. By schedule things like I just said, we're just gonna we can get the algorithm that that handle any number of updates in this update time. Yeah.
I'm a bit confused with what you mean by worst case update time, because this year worst case update time is
You asked what is worst case update time?
yeah, I'm a bit confused because if worst case update time at any point is T, it's TU and everything.
Is T no like the time this is the time that we spend.
No, it's like not here, just what's TU, I don't understand.
TU is the update time for the data structure.
It's an upper bound on the update time.
It's the upper bound on the update time for your black box.
Then why are we getting something even worse?
Why are we getting something worse? Because review time here is really big. And now we used to get something like TB over L plus TU amortized.
I don't understand. Why should you able just use TU?
Oh, because like the question you asked, like why don't we just use TU everywhere?
Yeah.
Because here I said that this algorithm can handle only L mini updates. Just like in maximum matching, we can manage to get simple algorithm only for amount of time.
No, I missed the first line.
Yeah.
So TU for the maximum matching is like 1.
It's like 1.
1.
Yeah.
Whereas TB was E by F steps.
Yeah.
But you can do 1 only for epsilon size of matching steps.
Yes. Yes. Yeah. Yeah. Again, yeah. For maximum matching, TB is like linear. In M, like in number of edges, TU is 1, and this is like epsilon times the matching size. Yes.
Could you just give some intuition on why we need the speed up phase where you process 2 queries at a time? Why can't you just have only 2 phases where you rebuild and for sometimes it's correct?
Why do we need like the yellow phase?
Yes.
Yeah, the answer is that once you are done with the red phase, you get a data structure that is just for the past.
I see.
So now it's the time to catch up.
Okay, okay.
By just feeding update at double speed. Good.
So
Yeah.
is it possible to use multiple such like A3 prime, A3 double prime, A4 double prime, and then get it up to 2TU phase?
2TU phase. Sorry.
So I mean here you're using two A1 double prime and A2 double prime, but
Yeah.
maybe I can use even more A3 double prime, A4 double prime, and have the sizes different. So that always someone is ready.
Yeah.
So after the catch up, is it possible to have some other? And parallelly you can run maybe 4.
Yeah.
In one case, other can catch up. But
Yeah.
that will,
I mean, you could make more copies, but like with asymptotic bounds, this is kind of enough.
So in the sense that you want to reduce the TU.
Yes.
Right now, you were upper bounding the number of edges by n squared.
Yeah.
If I want to keep that as a number of edges, can I get like square root of the number of edges over epsilon?
Yes. Like using this idea, you can get square root m. Yeah.
Currently we are splitting the TB step over L by 4, right?
Say again.
Currently we are splitting TB over L by 4.
Yeah.
Rates.
Yeah.
If we increase the L by 4 to a bigger number, trading off with adding more copies of the algo A, is there an optimal like trade-off between the number of copies and the?
I don't think you can improve this. Yeah. Let me. Okay.
Yeah, final question.
Yeah.
For the matching problem particularly, does it help if you have many maximum matchings? Or like somehow, I mean, not for this, I mean, this template I understand, and like somehow, as you said, this is like, in the matching example, like if you say have many multiple, like the dense graph case, the n is large, but the fact that you have many maximum matchings, many near maximum matchings, does it help? Like somehow, it's hard to imagine that all of them get sort of killed or.
I don't see why making more copies would help, but let's discuss this later. Okay. So now what we get now, right, is just we can maintain at least the maximum matching size in this time. Worst case now. And you can think for the exercise how to get better worst case update time to be like maybe like max degree of the graph. So there's some hint, but I make it hard to read.
But isn't this exactly what you did? You just substituted that with n and m.
Yeah. Yeah. You get the point. Yeah. Okay. So now let's go to the next template. Okay. So this has been used by Monica and Barari, and then many other papers. Okay. When people call batching, this is what they mean. Let's see what it is. Okay. So the running example here is another problem called decremental connectivity. So in this problem, you have a graph initially with n vertices and m edges. And then let's say you only have edge deletion only. This is not going to be crucial. I just get deletion only just for simplicity of presentation. And we want to ask if the graph remain connected at all time, at each time step. Again, for any problem, you can do it from scratch, How fast can you compute if the graph is connected from scratch? Linear time, BFS, something like that. But yeah, let's see how to get n to the 2/3 now. Okay. So the idea behind batching techniques is based on one batch version of the problem. So given any problem, we're going to consider one batch version. So what is this? The setting for one batch problem is that, okay, and one batch is often just going to be easier to design. Yeah? So for this problem, you have a graph, and the update is not a sequence. It's not a sequence of onlines. It's not an online sequence. It's just a single batch. A single batch D of DH deletions is given to you one time, and that's it. And then you just need to answer if the graph G prime after deleting D is connected. And that's all. Like it cannot handle another batch, just single batch. Okay, so what we will show soon is that we will see how to design a one batch algorithm, A batch, such that the initialized time is linear in M, update time is D squared. So if D is small, then this is like small. Okay. Let's assume this as a black box for now, and let's see that how one batch algorithm can give you dynamic algorithm that handles sequence of updates.
So when you say update time, this is the update time to handle the entire batch.
Yes, this is the update time to handle entire batch of size D. Yeah.
Gotcha. So,
No worries. So, yeah. So let's see from here how to get this algorithm with n to the like sublinear update time. Okay. So the idea is simple again. Is to handle a sequence of updates. That this is what we want. We're gonna use one batch algorithm. So how to do this? Look at the ith update. Like here we get a sequence of update. Let's say that now we get the ith one. We're just gonna feed the whole batch from the first update. From U1, U2 up to UI. Now that's the one batch now. And feed this whole thing to A batch. So this is, for example, for us, is this whole batch is going to take I squared time. Okay. So what does it give us? It gives us some black box algorithm from this idea, right? Really simple idea. It gives us an algorithm such that if you want to handle L many updates at most, the review time is linear. This is just what we assume. The initialized time is linear. But the update time, for every update, it's going to take at most L squared time. Just the ith one, just revert everything and give the whole batch from update 1 to update I. That takes I squared. If there are just at most L updates, that's L squared update time. But from here, we know how to get dynamic algorithm. This can handle at most L many updates. But we know how to get dynamic algorithm that handle any number of updates. It's just gonna give us this. Because recall, right? Given this kind of black box that can handle L update, TB the review time, TU worst case update time, you get this time, TB over L plus TU. Plugging this in, you get M over L plus L squared update time. And then choose the balance the L, you get this. Yeah.
So, if I understand correctly, when you're looking at the ith update, you're looking at the history you want UI and fitting it up.
Yeah.
So let's go for the I plus 1. And it has got, again, you have to look at the history from U2 to UI plus
No.
1.
You look at, from given UI, you look back up to U1 and give this is a batch. For the next update, UI plus 1, you look back again to U1.
Okay. Otherwise,
Like the size of the batch just keep increasing.
It's kind of recompute from scratch of the entire batch.
It's kind of recompute from scratch, but you have a better black box. Yeah. You have like this one batch algorithm to recompute from scratch a bit faster. Yeah.
This one batch algorithm does not destroy information about the original.
It will not destroy anything. Yeah.
We at each instance we have exactly one copy of the original.
Yeah.
So what do you do when the batch ends? Like when you have L updates, what do you do at that point?
Oh, after L update, you just rebuild.
Okay.
Just like the schedule thing that we have seen before. Okay. So I hope this is clear. And now it's just about how to get this one batch algorithm. Okay, let's see. Let's now show this A batch algorithm. Okay, so here's the idea.
Like, as you were saying, this is like a template that instead of a per round update, if you give me a batch algorithm, that will give me this TB. That I can use it to get this
Yeah,
TB.
this is a template that given for any algorithm, if you have one batch algorithm, you get dynamic algorithm immediately. Okay. So let's now get this one batch algorithm, how to get it. Okay. So in the initialization time, I just compute some spanning tree. This is this tree T. And now let's say there is one batch, like the update batch give to you. Looks like this deletion. Okay. It deletes things in the graph. But when you delete this, it will kind of split your tree into parts. For example, here it split the tree into 3 parts. And like the number of parts is going to be like something like d prime, something at most d plus 1. So now what is sufficient for you to do? Your goal is to check if the graph remain connected. So it's just enough if I can find if there is some non-tree edge connecting each of the parts. If the non-tree edge, they connect the parts into one component, then yeah, I'm done. That's all I want to do. So for between each part, Ti and Tj, check if there is some connection. If I can answer this for every pair, I'm done. So now we're going to show how to find these edges, how to detect whether there is some edge between Ti and Tj. And we need 2 tools that is standard in graph algorithm, Euler tool and range query. So let's start with range query. So like this is a 2D like 2-dimension range query data structure. It's just a data structure that you get a point set in 2 dimensions, like here. And you can update by inserting or delete a point in something like log square time. If you just use range search tree, for example, I'm gonna just assume this. Okay? And you can also query by giving like some rectangle, some geometric rectangle, not like combinatorial rectangle like in the first talk today. Just some contiguous rectangle like this. And then you check if there is some point in the rectangle. So you can update and query like this in like logarithmic, polylogarithmic time. Let's assume this. And another tool is Euler tool. What's this? So it's a way basically to represent any tree as a path. Given any tree, you try to represent it as a path. See, let's say example, you have this tree. Then I can like walk like this and give you a sequence. That sequence looks like just this sequence, just by walking along the tree. So now it's like a sequence, so it looks like a path. So now what you should, like what we need is just that for every edge in the tree, it would correspond to 2 edges in this Euler tool. For example, if I look at this edge, 3, 4, just correspond to a walk from 3 to 4 here. From 3 to 4, and then from 4 to 3. Yeah. Each edge correspond. Each 3 edge correspond to 2 edges in the tool. Okay. So now we are ready to get this algorithm. Yeah. So the initialization, I compute a spanning tree, and then get the Euler tool. Yeah. Get this Euler tool. And we're gonna create this table. Get this Euler tool, put the row here, put the column here, put the row here. And the index is according to this Euler tool. And for every non-tree edge, we're gonna put a point in this grid. For example, like this is from 1 to 3. So let's say this is like this is an edge from 1 to 3. So look at the first appearance of 1, and look at the first appearance of 3 is here. Then I put this point and make this to be symmetric. Just do this for every non-tree edge. So with these three non-tree edges, we get this point. Okay. So that's initialization. And now, given the update, the batch B, what we do, like let's say I get this deletion. Like I delete this edge and also this 3 edge. So what we do first is just delete the point that corresponds to deleted non-tree edge. Like delete this guy. Now, next, when you delete this non-tree, now let's look at the deletion of 3 edge. It will partition interval. Partition this Euler tool into intervals. Like when I delete 2 from 2 to 3, I just gonna delete from 2 to 3 and 3 to 2 here. If you delete the edges, you're gonna split this into like 2 Ds, many interval. So we get this interval on the column and on the row. And now, note what is happening here. Like I'm just gonna query for every interval here. Like I get now like something like D by D grids. And just what we're gonna do is just to query for every interval, for every like rectangle in the D by D grid. Just check if there is some point there. This is not deleted. For example, this point, if I check, then it means that I basically kind of check whether like from this component, there's some, is there an edge to this component? And there is this point, so that corresponds to this non-tree edge. Okay. So basically, just by querying this rectangle d squared times, you basically check if there is some non-tree edge between every part of your tree, for every component of the tree that is split.
d squared by 2, right?
Yeah. Yeah. Okay. Okay. So that's the algorithm. So now let's analyze the time. Here is just linear time. Yeah. Spanning tree and add some point in this. You can add in polylog time. And this part it takes d time, but here you need d squared, many queries. So the total time is d squared. Okay. So that's how we get, yeah.
Then you have to add these, like you have to reverse, like you need to add these deleted points back to the table so that the next time you don't have to spend the initialization time again.
Right.
The next update.
Good. So you said that like after you handle one batch, and then in our reduction when the next update comes, do we need to revert everything that we have done? Yeah, we need to revert. And
That is already.
you can imagine that you can revert everything. Actually, this is good to know. For any data structure, you can assume without loss of generality that you can revert it using some techniques called persistence. Some black box, but you can revert it by hand too. Yeah.
The Euler decomposition, a single component may exist as multiple intervals. Right? Once you have deleted some edges, a single component may not be a contiguous interval. May have
It will correspond to like two interval at most.
no, if there is a tree and there is multiple edge deletions, then there can be multiple smaller intervals, right?
Okay.
Yes, that's why you said it's a D cross D grid.
Yeah, you get D cross D grid.
I'm saying that when you combine them, you have to make sure that, so in case of an Euler 2 tree, when you're doing an Euler 2 traversal and you're deleting the edges, then every interval in that grid does not correspond to the complete connected component. There might be multiple intervals that are still connected without the non-tree edges as well, right?
Okay.
So suppose there is a tree which has a multiple span, and Euler 2 tree, Euler 2 comes something like this, and there are some edge deletions here. So it shows here that this interval, this part and this part, all of these three are separated the grid, but they are actually connected by the same tree, right?
I don't quite understand, but let's take this offline. Yeah.
For this particular problem, do we need a rebuild phase? Like the algorithm that you said, D square and do rectangle searching. Can't we just add like another order of T more rounds or something and use this to rebuild? Like, do we need a separate rebuilding algorithm, or is it like, isn't it just enough to modify this algorithm? So if you want to construct a new spanning tree.
Yeah.
And let's say I find 1 point for each of the D square rectangles. Can't we just use that to rebuild a new spanning tree?
How to rebuild a new spanning tree? I don't quite understand. Sorry. Can you repeat again? Yeah.
So we started with spanning tree.
Yeah.
And then we have this Euler too. So at the end of crossing all these, like at the end of crossing the batch, let's say we found that the graph is still connected.
Okay.
Can't we use the information that we created while processing it, all these rectangle search queries, to create a new Euler too? Because we found the edges that we need.
You try to speed up by okay.
Like, is there a separate need for a?
There might be a way to speed up, but I don't think it will be easy. Yeah.
Sorry, your 2D range search thing, instead of where is this Boolean answer is like whether such a point exists.
Oh, you can report a point.
You can also
Yeah. Okay. So what we get so far is one batch algorithm, initialization time n, update time d squared. And just by plugging in into our machinery, we get this sublinear worst case update time. Okay. I want to make a remark that, okay, if you get this thing better from this square to d, then immediately you would get this to root m. And actually there is an algorithm that get d here. So you get root m immediately too. Okay. And here's an exercise. If you really think, like, to understand this, think of this offline. Okay. So imagine that you have a stronger black box, not just one batch algorithm, but two batch. What do I mean? I mean an algorithm that get a graph can handle a first batch of size d1, and then it can handle another batch too of size d2. And at the end, you can answer if the graph is connected after these two updates. Exercise this. Suppose that you get the algorithm that handle the first batch in this time, d1, and the second batch is take time d2. So this is important. Like, you suppose that I think like d1 as this size and d2 as this size. The second time that you handle a smaller batch, you should spend time proportional to the smaller batch, not the first batch. If you have this, then show that you can improve this further from root m to n to the 1/3. And if you have k batch, say, algorithm, then generalize this to this update time. This is the template that is used in literature, actually. The notable example is something called expanded pruning. You can look up what is this. It's a key tools to make people enable to use expander in dynamic algorithms. Okay. All right. So, but I just want to make another remark that most of two batch algorithm does generalize to k batch. Like one batch usually is easy, two batch quite hard. If you can do it, you can make it work all the way. And what we see today is one batch algorithm that actually is not going to be clear how to generalize to two batch. And you can think why. Yeah. Like the short answer is like, when you get Euler tour of the initial tree, if you cut it into intervals and you get a new tree, it's not clear how to build a new range search for the new tree fast, because you cannot move the whole interval around. Yeah. Okay, so good. For connectivity, we do have algorithm that can handle any number of updates in polylog time, actually. So there is a way, yeah.
It's like that. So is there connections in the other direction too? That is, if you assume, like, let's say I look at this login update for connectivity, do I get interesting insights into range search?
Oh, you asked if that, like, here we can show reduction from connectivity to range search. Yeah. Is there another way? I don't quite know, actually, but I would expect that it shouldn't be the case, because like the geometry of graph usually is just it's more complicated than 2D. Yeah. Okay, so that's basically two templates that we have learned, and the third template we're gonna continue on after the break. Okay, so yeah, thanks. Yeah, 4:30.
No, so someone needs the full 1 hour
Yeah. Yeah, please come at 4:30. I need 1 more hour. Hey, good to see you. Yeah. How are you? Yeah.
Sorry, I didn't made myself clear at that point. So the question, are you free? Yeah. So the question was, when you have an Euler tree, let's say you have any spanning tree, right? There is no kind of a limit on kind of spanning tree that you are considering. And let's say there are some edge deletions here. So this upper part.
What is it? I don't understand.
Can I make it?
Yeah, you can write something.
Okay.
Or you can. Yeah. Fire or mimicking networks. Right? The setting is this. Imagine you have a huge graph, and then there is like some small set of terminals S that you care about. What you want is to compress it. You want to get a graph H such that, well, first it should contain your terminal set S, and then the size of your graph should be close to S. Graph is huge, small set of terminal, you compress it to just the size of the terminal set. But H still preserve information related to S. So I use this notation. H is basically similar to G with respect to S. So we call H a specifier of G with respect to S. And here's one example that exists. Robotic specifier for shortest path. So for any K that you can choose, given a graph G, you can get H such that the size of H is something like close to S times something small. Think like K as 100, for example. S times something small. And yet, for every pair of nodes, UV, in the terminal set, the distance between U and V is preserved up to K factor. So this is possible. I'm going to tell you how. We're going to look at another one that is simpler. It's a vertex specifier for min-max path. So what do I mean by min-max path? I mean, like, ST min-max path, yeah, it's just a path from S to T, such that it has minimum. It minimizes the maximum weight. For example, from S to T here, what's the value of min-max path? 7. Yeah. The shortest path would be 10, but the min-max path is 7. Okay, good. So now one really nice thing to note is that if you look at the minimum spanning tree, it actually preserves all min-max paths in the graph. So what I mean is this: like if you have a MS3 T, and if you look at like this, if you look at any S and T, there is a unique path in the tree from S to T. There's always a unique path. And that path is going to be a min-max path from S to T in G. So like a minimum spanning tree is a really good specifier when you care about min-max path. So let's prove this quickly. Yeah, this is the claim. The path from S to T in T is a ST min-max path for every pair ST. So suppose that is not. Suppose not, then there exists another path, P prime, here. Let's say P prime looks like this, such that it's better somehow. So if you look at maybe like the maximum weight edge, the heavy edge in this path, maybe the heavy edge has size 9, then the weight in the purple part of P prime here is just going to be all smaller than the red one. But if you have this, then you get contradiction, because you can look at maybe like a tree, the blue tree like this. In particular, you can like add this edge here, and you remove the red edge, and you get a better spanning tree. So that's contradiction. Okay. You can add some edge in the purple one, and remove the max guy. That's contradiction. Okay. So.
Sorry, can you see the general definition again? So one slide back.
What is min-max path? You have?
Not what is min-max path. One slide back. What is the general notion of this classifier?
Okay.
What are you trying to preserve in general?
I want to get a vertex specifier for min-max path.
No, I understand, but I'm saying in general. So can you just go one slide back here? Sorry.
Yeah.
I see. You don't have it. Okay. I see. So you have some function on S, and then you want to preserve that.
Yes.
Okay.
Yes.
All right. Thank you.
Sure. Yeah. So far, there is no S in this slide. In this particular slide, it just specifies H. Yeah. Given any graph, you can get a tree. The number of nodes are the same. But yeah, just remember this for now. MS3 preserve all min-max path. So now, but we want not just to specify edges, we want to specify vertices. Let's do that. So let's say you have a graph now, and now there is some terminal set. What we want is to get a graph hash such that the size is close linear in S, and for every pair between every terminal pairs, the min-max value is preserved. So I mean like hash is equivalent to G with respect to S when you care about min-max value. So let's start with some warm-up. Suppose that your terminal set has 2 nodes. It's just U and V. This is the terminal S and T. U and V. Yeah. And how should your graph hash look like? Just the path from S to T. Can you simplify it a bit further? Just a single edge. Take the max guy in this path. Take the max guy in this path. That's one edge. That's a vertex specifier. So here just take one edge.
So we are allowed to have edges in H that are non-edges in the original.
Yeah, we allow to use any edge in G here, in H here. Yeah, it doesn't need to be subgraph.
Okay. And the final vertex set of capital H does not have to be just S. It can use other vertices.
It can, yeah. H can contain something outside S. Okay. So in this case, 2 terminals, that's simple and nice. Let's do it for any set. The algorithm is you first compute minimum spanning tree, and you can just now care about this minimum spanning tree. It preserves all min-max path anyway. And this is your set S. What we can do is we try to reduce the problem to the path version. So we're just gonna compute like LCA closure of S. So for any nodes here, look at LCA, add it. Look at LCA of this guy, add it. So just keep adding LCA until like there is nothing new you can add. Yeah. What's the size of S prime when you add all this LCA? It's still gonna be like 2S. Okay. So the size of S prime is 2S. Now what we can do is like we kind of look at each adjacent UV in S prime. Like for example here and here, these are kind of adjacent. There is no other S prime in between it. And we can simplify this guy from A to C into a single edge, because it's like you can just, if this is like if you have many edges here, just put a number, the maximum guy here, and do this for every adjacent pair of S. That's it, you're done. So the correctness is kind of clear. It's just kind of, it's because MST preserve all min-max path. And now you just reduce the problem to the path case, where you can just contract the path into one edge. And the time is linear, the size is linear in S. So that's good. That's how we can get vertex specifier. It's nice and simple. Okay. So now I want to we want to consider one really nice property of like something called composability. So I said that this similarity relation, I said that it's composable if, suppose that you have some graph that H that is similar to G with respect to S, and if you look at any edge UV where the endpoint are in S, some edge, arbitrary edge, but the endpoint are terminals, then I would say it's composable. This relation is composable if when you just add E into both sides, then it's still similar. If this is true, if you get first and second thing, and then this side is true, then I say it's composable. Now this min-max relation is composable. Right? Let's see why. Suppose that you have H is similar to G with respect to S. Now let's look at any pair ST, the terminal ST, and let's I want to say that min-max from S to T in G plus E is going to be the same when this G is replaced by H. Okay, so why is this? So first, let's analyze this thing a bit. What is min-max of G plus E from S to T? What can it look like? So when you have a graph G, there can be like all min-max path here. Now you add the new edge, E. What can the new min-max path look like? First, it can be just the old one. The new edge might not be useful. The second case is like maybe I go through U and V, and then from UV to T. There's a third case, which is to V first, and then to U, and then to T. So that's the three cases here. Okay. So now when you look at these three cases, it kind of represents min-max in G plus E in terms of min-max in G. But H is equivalent to G. So I can just write this whole thing. Anything that subscript G, I can replace it by H. But this is just the same as min-max in H plus E. So what do we show? We show that if h is equivalent to g with respect to h, with respect to the terminal set S, I add any h. H plus e is still equivalent to g plus e. Good. Okay. Yes.
So if you were looking at h as a sort of function of g, so instead of h plus e, take h prime, which is generated by the algorithm we discussed from g plus e. Then this need not work.
What need not work?
Then this similarity would then that so h prime need not be equivalent to g plus e. Sorry.
It must be.
Okay, right. That's just by algorithm's correctness.
Yeah.
So h plus e here is not h prime.
Yeah, it's not h prime. It's just h plus e. Okay. All right. Yeah.
Possible that in H this becomes a non-simple path. Some edges have to be repeated. Yes.
I don't hear you. Sorry.
In H, in the reduced graph, this path becomes a non-simple path because they have to repeat some vertices to it. Is that correct?
The path can maybe not simple. That's okay. Yeah.
It doesn't worry.
It doesn't worry me. Yeah. Okay. So that's the background, and now let's see how this notion of vertex specifier, how come it's useful for dynamic algorithms at all, right? So far it's used, it's nice, you compress things. Why is good for dynamic algorithms? So this is used in like many many recent work, and also in all of modern math flow algorithm, it used this kind of thing. The first work that used something like this is the one by Einstein. At least what I know. Yeah. Okay, so here's the plan. What I'm gonna do is I'm gonna show reduction that like given any fast algorithm to compute vertex specifier from in max path, then we're gonna get offline dynamic algorithm from in max path. This template just works actually for any problem. Then I tell you like how to get actually non-offline, the better one, the strong one. I tell you soon. Yeah. Yeah. Okay. So yeah. What is offline? Yeah. So offline version is this. Imagine let's assume for simplicity of presentation right now that like at each step, instead of I get some update or query. Let's say that the user just gonna both give me both update and query. Just make things a bit harder. Just to simplify notation. And now by offline I mean this. I mean that the input is not an online sequence of update or query. Actually the input that is given to us is the whole sequence of update and queries. So this is what I mean by offline. Like you get the whole sequence of things. This sequence still have a notion of time. Like at time I, you get a query I, you want to still answer the graph, answer something about the graph at time I. But you get a whole sequence of updates to you. Okay. So what we need to do is for our I, then we want to compute, let's say, min max between Si to Ti in Gi. Okay. Trivially, again, any dynamic algorithm, you can do something trivial by computing things from scratch. Offline version is even just easier. So you can do it in m squared time. Each time spend linear time. For each time step, spend linear time. But we're gonna see how to get n to the 1.5 and then m later. So this is the offline time. So if you think about it, you should read this as basically like close to constant time per update. So that's the goal. Okay, so what's the idea? Our idea how it connects to vertex specifier is this. For every time step I'm gonna compute vertex specifier hi that is equivalent to gi with respect to the thing that I want to query. Okay. So I just compress the graph gi to something tiny hi of size constant. For every time, every graph gi, compute something tiny that preserves information about what I want to query. So if I have this, then I'm good. But why? Because what you can do to compute min-max value in S from Si to Ti in Gi, you can just query this in Hi. It's the same number. But Hi has constant size. So for all I here, you can compute all this thing, compute the value here for all I in linear time. Instead of m squared, now you get all this value in linear time. Okay. So if we have all the hi here, we're good. But that's the idea, like why vertex specifier is good. Now, the trivial way, like one way just to compute, the question now is just how to compute this hi for all I. And the trivial way is just for every time step, gi compute gi compute hi, gi, and the next gi compute hi. You spend linear time per I. That's bad. Like the time to compute all this hi is m squared. So the goal is, okay, we're gonna improve the time to compute all this hi. I'm gonna show you some picture in high level, tell you the details soon. But in high level, the picture looks like this. We're gonna kind of divide the time step into chunk of root m interval of size root m. And then in each interval, we're gonna spend linear time still to get some graph here. But we do it only like as a root m interval, like root m, like we do it only root m many intervals. And then like for each of the interval, we're gonna do something more fine-grained. But the next time step here, like this time, it's gonna be root m per time step. And the total time is gonna look like m to the 1.5 instead here, because there are m, like this is like m, but there are root m interval. So this level is like m to the 1.5. Here, there are m many arrows here, but each of the arrow you spend root m time. Okay, super high level. Now let's see how to do something like this.
Sorry, just to clarify. So in this picture, the G2, G3, these graphs will not be even processed.
Yeah, we see soon. Yeah, this is just some sketch. Yeah, we will consider it somehow. All right, let's see the details now. Okay, but before that, I need some notation. So, right, we're gonna divide the timeline of size n to root m size. There's gonna be interval of size root n. So divide this update sequence into interval of root m size. For each interval I, like this, there's gonna be some, like there's gonna be, okay. For interval I, this looks like this. So now consider any edge that is that is in your graph. For each edge, that edge will have its own interval as well, right? It's just the time. Let's say an edge is inserted at this time, and it's deleted at this time. That's the interval of this edge. Okay. But now we can kind of categorize the edge into two sets with respect to I. I say that the set of permanent edge in with respect to I here is just a set of edges such that the interval I is in I of E. So the edge is kind of is there forever with respect to this interval. Any edge that kind of there forever in this interval, that's the permanent edge. Now there is another one which is like the edge, the updated one. So there is a one such that the edge set such that its interval is still intersect with its interval IE intersect with I, but not the whole interval I. Like this. So the edge can stay inside or like overlap like this. That's the updated one.
Most edges are permanent, right? M minus 2 10 edges are.
Yeah, that can be like order of M permanent edges. But the updated one, that's small. That's root M at most. Because yeah, each time we update at most one edge. Okay. Now, to talk about vertex specifier, we need to define a terminal set. I will define a terminal set with respect to this interval I to be the endpoint of the updated one, the endpoint of the green guy here, and also the endpoint of the query. For each time I query some SITI, so that set here is gonna be in my terminal set. For example, like this guy are the one that is updated in this interval. I also kind of query this one. So the interval is just the endpoint of this guy. It's kind of the guys that kind of you care about.
So just to make sure, we are maintaining the list of permanent intervals for every single capital I?
Yeah. Say again, sorry.
So are we maintaining the list of permanent intervals for every single capital I?
I didn't tell you yet about algorithm. Here is all about definition.
Okay, sorry.
Yeah. I don't hear you.
Can you say the terminals once more?
The terminal SI is the endpoint of the updated edge with respect to this, and so also the endpoint of the queries. Like here, like just this is the endpoint of the green guy and the endpoint of the query.
Terminals do not lie within the interval. With the right to itself.
Terminal might not what again?
Take. Oh, okay.
Good. Right. Okay. Now the algorithm. Okay. We're gonna get n to the 1.5. Yeah. So the algorithm is this. We're gonna do the same thing for every interval. Let's look at one interval I. For each interval I, the first thing we do is to build some specifier that preserve information about permanent edges. Only permanent edges. With respect to this terminal set, the guy that you care about. Okay. So you get some graph, hash interval. The size is going to be of size root n. Because the terminal set is of size root n. Okay. But note that this graph hash interval doesn't have the green guy. We forget about the green guy here in hash interval. Okay. Now, for every fixed, like this is kind of the crude one, it's about the whole interval. Okay. Now we're gonna try to look at one point of time, I. Look at one index I, step I. Now we're gonna look at the graph, like h insert I is just the graph like from this h interval where you add all the edges, the updated one. So like the guy that, okay. So what I mean is this. If I look at this graph at time step I, right? Okay, all the permanent guys are already there. There are some updated edge, but only this guy should be there at time step I, not this guy. Okay. So these two edges maybe correspond to these two edges, not all the updated one. So this is the edge that should be there at time I precisely. So just add these edges to h interval. That's hi insert. So it's kind of the graph where like you start with the crude graph, h interval, and now like you add edges that you missed for time I. And lastly, you get this graph h insert after inserting this yellow edges. Now you just compute the vertex specifier of this guy again. It's the vertex specifier of vertex specifier. You compute hi to be vertex specifier of hi insert. Now only with respect to the endpoint that you care about. Now like from this guy, from this h insert, compress it to just the graph of constant size. It will contain SITI, and the whole size is now constant. Okay.
So second step, HI insert is HI interval union there. So
Yeah.
the number of vertices in HI insert could be more than HI interval, because if GI minus EAP
No,
had an effort.
HI, like you asked, like you worry about like, can this guy add some new vertices into the graph? It's not going to be the case. Why is that? Because HI interval is with respect to this SI.
Okay.
SI contains all the endpoint of the guy that you might insert.
Oh, okay.
So like the edge here that you add is going to be like the endpoint of this edge is going to be already there.
I see.
Yes.
Do you think HI is just equivalent to computing the min-max?
Yeah, HI will be equivalent to GI. We will prove this.
It will just be one edge, right?
It will be one edge, yeah. HI will be just one edge. Yeah.
This is composability because of composability.
Yeah, it was because of composability. Okay. We're gonna analyze this, but at least is the algorithm clear? Okay, let's analyze. What do we need to show? I need to show that like for all I, hi is equivalent to gi with respect to the pair that we care about at time I. If we do this, that's the goal, right? If we just want this for every I. Once we have this, we can query the whole thing later. But this is the goal. So let's do it step by step to prove this thing. So the first thing I want to show is like the intermediate step. I want to say first that hi insert, the big guy, the quite big guy, not linear size, but root m size guy, is equivalent to gi with respect to this terminal set Si. So why is that? Well, first, I just start from here, right? We get this crude graph that preserves the terminal set, H set in the interval. But now, given this one, by composability, I can just add the yellow edge set into both sides. Because this relation is composable. If I add the yellow set to both sides, it's still equivalent. So what is this? That's HI insert exactly. What is this? Just GI. So we're done. Okay, so note now that like HI insert is equivalent to GI with respect to SI, to like the whole set of the purple nodes here. So if it preserves all information with respect to like all purple endpoints here, it would preserve information about SI and TI, just 2 points, because as this guy contains the thing that you query. But you also know that like from this step here, HI is equivalent to HI insert. So just combining these two steps, you get that HI is equivalent to GI with respect to the endpoints SITI. Okay. So that's it.
Why do we compute HI? Like, why can't we just stop at HI insert and then answer the queries?
Oh, we could do that. Yeah, we could do that. I just kind of try to say this so that you'll see how to do it, how to improve it further later. Yeah. Okay. Okay, let's analyze the time. There are root n loops here. This guy, you cannot compute vertex specifier of the whole graph. That takes linear time. How about this? There are m loops in total. But each of the time steps, you cannot work on the graph of size root m. So that's root n time. So in total, this is like n to the 1.5. So what do we get so far? We get that like, given all the GI, we just show how to compute all the HI, such that HI is equivalent to GI with respect to the query at time I. In total time n to the 1.5. And once we have this, right, we just can query all the query on top of HI. For each time I, we get an answer in constant time. So that's how you get all the answer in n time after that. Okay. So that's how you get n to the 1.5. But from here you can get it further. You can improve it further. Why? Because the idea was that previously you compute vertex specifier of vertex specifier. You can repeat, just make more layers. So from 2 levels of specifier you get this. If you think about it, exercise here. Make k levels of specifier, you're gonna get to this time in total. Like, yeah. And if the problem is about some approximation, then the approximation that you get at the end is like getting worse by like k, like power of k. But for today, everything is exact. Yeah, for us, this is exact. So by just setting k to be log n, just improve from n to the 1.5 to nonlinear. Yes?
So the reason why this algorithm is offline is because we need to know the sex SI.
Exactly. Yeah. This is offline because we need to know. For each interval, we cannot look ahead for root m steps. Where are the endpoints that we care about?
Okay, if you could guess SI somehow intelligently or something.
If you can guess SI, then you can, yeah, it works. So let me conclude. We just saw a black box transformation. Right? That given a fast vertex specifier algorithm, you get fast offline algorithm. Actually, even fully dynamic. Yeah. Okay. But actually, this idea carry out to like non-offline version too. I just gonna sketch, like, say something high level. Yeah. How can this be possible? So basically, if your vertex specify algorithm can do something a bit more, not just like static problem. If it can handle some operation that is about add terminal. So I have vertex specifier, it compresses the graph to something small. But I can say that I add one more terminal. I get still a small graph, but maybe a bit bigger because I add more terminal. But I do this in time that is fast, not do this from scratch. If you can do this, actually it will give you in the black box way to incremental algorithms. If you can handle add terminal and delete, by delete here, I don't mean add terminal, I mean delete edge. Delete terminal may be a bit harder, but like delete edge is actually simpler. And if you can do this, you get fully dynamic algorithm. This is how people get like modern dynamic algorithms.
What's the difference between dynamic and fully dynamic?
Fully dynamics mean you can handle both insertion and deletion. Incremental, only insertion. Okay. And like, if you like just kind of by looking at the literature on vertex specifier, many times you kind of don't need to do anything. Like understand the algorithm, and you actually can see how to support add terminals easily. So you can get this kind of easily, like automatically, many times. So now here's some open problem in dynamic vertex specifier. I think it's like kind of still a rich area. So everything that is highlighted.
There's a question.
Yeah.
Is there a particular structure to the problem which makes it sparsified?
Which problem is specifiable? So far, anything that is about flow or distance, usually that you can specify up to some approximation.
Should always have some min-max flavor, or?
Oh no, like for example, like distance. You can do it. Even max flow, you can like approximate max flow, you can do it. Yeah. So we're gonna see. This is an example. So we see this min-max path, but something is known about shortest path. Something is known about C connectivity. Like, is the min cut at most C or not? Max flow, even effective resistance, which is about flow, but like this guy is about like kind of L1. This is about L infinity. This is L2. Whatever that means. Yeah. So many things is known. Many things is not optimal. A lot of things to do. Okay. So let me conclude. So what we have learned, right? We see 3 templates. How to design a graph algorithm. The first 2, classical. This last one, quite like a bit newer. And along the way, like at least I hope you learn this kind of simple terminology. Worst case, amortized of that kind, fully dynamic, partially dynamic. One batch algorithm. This is a notion that has many names in literature. People can call it sensitivity oracle or emergency algorithms or fault tolerant data structure sometimes. An offline dynamic algorithm. This is the thing. So what are the 3 things? First, rebuild in the background. The second, batching. So given one batch algorithm plus rebuild in the background, you get dynamic immediately. And if you can make it work for k batch, then you get better dynamic algorithm. This is used in like some papers. this vertex classifier that you just have seen. We have seen the 2-layer version. Exercise to think what to do in K layer and make it work. Okay. So there are more things. There are more templates, not just 3. Yeah. So the recent and quite nice template that is developed in the last few years is optimization method for dynamic algorithms. So one quite nice thing is here. It's about designing static. It's kind of robust against updates. Just for example, when you compute flow, you want maybe to spread the flow to make it balanced, so that when you delete something, then when the user adversary deletes something in the graph, then it kind of hurt your flow only a little because you spread the flow. That's what's going on there. And how people formalize this idea can compute a solution that is regularized by entropy, maximize entropy somehow, and then it's useful for dynamic algorithm. So it's about identifying static problem that is just good for dynamic problems.
But if there is a unique solution which does not have the regularized property,
so you change the problem. The problem might have unique solution. You change your objective to optimize for entropy a bit, so that your solution looks like something that's spread out. Yeah. So that's how people use it. And there are a way to look at optimization method that is used everywhere and then make it dynamic. You have heard of multiplicative weight update and integrated point method. By now, people actually I should add a more citation here. The recent max flow algorithm, basically it's to make the recent max flow algorithm that takes almost linear time, extend quite seamlessly to dynamic setting by dynamize the integrated point method. Okay. There are other template if I give you incremental algorithm, I get fully dynamic offline algorithms. If I give you decremental algorithm, you can get fully dynamic algorithm for some problems. And for any decomposable problem in some sense, many geometric problems range searching, quadtree or something else. Yeah. You can get, if the problem is decomposable in some formal sense, there's a black box say that, okay, if that's the case, you get dynamic algorithms. Okay, I just want to mention that there are more things. Okay. Last slides. There are other generic techniques that is kind of useful for dynamic graph. One technique that I want to mention is expander decomposition and hierarchy. So this is used in, by now, more than 20 papers. I have some tutorial in YouTube with this link. You can have a look if you are interested. I have a course about this too, but there's going to be updated version of this course. This is 4 years ago. I will update, I will put it online, the new one, in 1 or 2 months. Okay. Another one is the edge degree constraint subgraph. It's just a keyword that you can look up. But what it is a subgraph that, in some sense, preserves very good information about maximum matching. It's useful. It's first identified and used for dynamic matching problem, but turns out that it's useful for many other models: streaming, communication complexity, fault tolerant data, like fault tolerant data structure. Yeah, so you can have a look. And randomized greedy techniques. This is kind of general approach that is useful for other dynamic problem like dynamic maximum matching, dynamic independent set, and I put a link there too. And yeah, we will upload this slide. Yeah. Okay, so yeah, I hope that you learned something, and yeah, thanks.
Are there any further questions? Okay. If not, let
One
us.
question, let me ask. So you mentioned about flow sparsifier, but there was some paper I remember like which showed Robert Krausgamer showed that flow sparsifiers are not possible or something with ball size. So what is the connection here?
Yeah, so okay, so here is about approximate. We're gonna need to pay some approximation. Then it's kind of quite big. Yeah. And but like there are many works on showing lower bound for exact flow specifier or even constant approximation maybe. No, I think the lower bound is known for exact only. I think. Yeah.
Exactly.
Yeah. Yes.
Archibald, are there any say connections to first let's say distributed algorithms here and even to temporal graphs or binary graphs?
Yeah. Is there a connection to distributed algorithm or temporal graph? For temporal graph, I don't quite know. But for distributed algorithm, vertex specifier has been used in distributed algorithms, like distributed reachability and like some other flow problem. Yeah, yeah, it has been used there. Yeah. Like they call it hub or something. Yeah.
But these techniques may not directly.
Yeah, like this is. I mean, they really use vertex specifier in distributed algorithm. Yeah. Any questions?
Thank the speaker one more time for such wonderful talks after landing at 3 a.m. today.
Something for coffee. You need it.
Yeah.